డేటా స్ట్రక్చర్స్ అండ్ ఆల్గరిథమ్స్ చదవాలి ఇప్పుడు. థింగ్ వచ్చేసి ఇప్పుడు ఇది డేటా స్ట్రక్చర్. Data is a collection of raw, unorganized facts and details like text, observations, figures, symbols, and descriptions of things, etc. Data can be recorded and does not have any meaning unless processed. Information is a processed information. Information is a processed organization and structured data. Definition of data structures. A data structure is a collection of data generally organized so that the items can be stored and retrieved by some fixed techniques. Classifications. Primitive, non-primitive. Primitive ante integer, examples integers, real, characters, pointers, logicals. And non-primitive ante linear and non-linear. Linear ante linked list, stack, cube. Non-linear ante graph, tree. And data structure operation. Insertion. Add a new data in the data structure. ఎగ్జాంపుల్ 10, 20, 30, 40, 50 ఉంది, కొత్త డేటా ఉంది. దీన్ని 40లోకి యాడ్ చేసి ఇంటర్సెక్షన్ ఆఫ్ డేటా స్ట్రక్చర్లో 10, 20, 30, 40, 50 అన్నీ ఉండేటట్టు చేయడం. డిలీటింగ్. రిమూవింగ్ డేటా ఫ్రమ్ ఏ డేటా స్ట్రక్చర్. డిలీటింగ్ అంటే ఏంటి? రిమూవింగ్ డేటా ఫ్రమ్ ఏ డిలీటింగ్ స్ట్రక్చర్. ఇప్పుడు 10, 20, 30, 40, 50 ఉంది, దీని నుంచి 50 తీసేస్తే అది డిలీటింగ్ అనమాట. సార్టింగ్. అరేంజింగ్ ద డేటా ఇన్ ఇంక్రీజింగ్ ఆర్ డిక్రీజింగ్ ఆర్డర్. 20, 30, 10, 5, 6 ఉన్నది, 5, 6, 10, 20, 30 ఇది సార్టింగ్. సెర్చింగ్. Final the location of data in the data structure. Example 5, 6, 10, 20, 30. Search of 10 a of 2లో ఉంది. ఓకే. 5 అనేది a of 0లో ఉంది, 0 లొకేషన్. 6 అనేది a of 1 లొకేషన్. 10 అనేది a of 2 లొకేషన్. 20 అనేది a of 3 లొకేషన్. 30 అనేది a of 4 లొకేషన్. Merging. Combining the data of two different sorted files into a single sorted. Example 1, 2, 3 ఇది ఉంది, 4, 5, 6 అనేది సపరేట్. 2 డిఫరెంట్స్ ఉంది మర్జింగ్లో. రెండు డిఫరెంట్ అని ఇవి రెండు మర్జ్ చేసి 1, 2, 3, 4, 5, 6 రెండింటిని మర్జింగ్ చేస్తాం. ట్రాన్స్ఫర్స్. యాక్సెసింగ్ ఈచ్ డేటా ఎగ్జాక్ట్లీ వన్ ఇన్ ద డేటా స్ట్రక్చర్ సో దట్ ఈచ్ డేటా ఐటమ్ ఈజ్ ట్రాన్స్ఫర్డ్ ఆర్ విజిటెడ్. ఇక్కడ 1 నుంచి 2కి వెళ్ళి, 2 నుంచి 3కి వెళ్ళి, 3 నుంచి 4కి వెళ్ళి, 4 నుంచి 5కి వెళ్దాం అంటే అన్నిటికీ టచ్ చేసాం. సో అన్నిటినీ విజిట్ చేసాం. సో అన్నిటినీ యాక్సెస్ చేసుకోగలిగాం. అదనమాట థింగ్స్. అండ్ అరే ఇన్ డేటా స్ట్రక్చర్స్. అరే ఈజ్ ఎ ఫిక్స్డ్ సైజ్ సీక్వెన్షియల్ కలెక్షన్ ఆఫ్ డేటా ఐటమ్స్ ఆఫ్ సేమ్ టైప్. అరే ఈజ్ ఫిక్స్డ్ సైజ్ సీక్వెన్స్ కలెక్షన్ ఆఫ్ డేటా ఐటమ్స్ ఆఫ్ ద సేమ్ టైప్. అరే ఈజ్ ఫిక్స్డ్ సైజ్ సీక్వెన్షియల్ collection of data items of same type. Access a particular element is equals to array name of index int a and box brackets. Data items are stored in continuous locations. How data is to be accessed. How you can calculate the address. int a of 5, 0, 1, 2, 3, 4 అనేవి లొకేషన్. 6, 2, 4, 3, 0 అనేవి డేటా బేస్ వచ్చేసి బేస్ అంటే లొకేషన్స్ ఇంటర్నల్ రిజిస్టర్ లొకేషన్ ఏంటంటే 100, 104, 108, 112, 116. a of 0 is equals to 6, a of 1 is equals to 2, a of 2 is equals to 4, a of 3 is equals to 3, a of 4 is equals to 0. తర్వాత address of a of I that is equals to base plus I into size of data type. I is equals to 0, 1, 2 and so on n minus 1. n is equals to size of array. So if want to I is equals to 2 int size is equals to 4 bit. 100 plus 2 into 4 that is equals to 108. int size and integer size ఎంత అంటే 4 bits ఉంటుంది. అండ్ ఫార్ములా ఆఫ్ అరే ఎంత ఉంటుంది అంటే బేస్ మీకు 100 నుంచి స్టార్ట్ అవుతుంది. ర్యాండమ్ యాక్సెస్ టేకింగ్ కాన్స్టెంట్ టైమ్ ఈజ్ టైప్ 1 డైమెన్షనల్ అరే, టైప్ 2 డైమెన్షనల్ అరే, టైప్ మల్టీ డైమెన్షనల్ అరే. నేమ్ లోయర్ బౌండ్ అప్పర్ బౌండ్ ఉంది నేమ్లో లేమన్ అరేలో. లోయర్ బౌండ్ ఈజ్ లెస్ దాన్ ఆర్ ఈక్వల్స్ టు అప్పర్ బౌండ్. ఎల్బి అంటే లోయర్ బౌండ్, యూబీ అంటే అప్పర్ బౌండ్. ఇప్పుడు ఇప్పుడు అర్రే ఉంది 2 3 4 5 6 7 ఇవి అర్రేస్ అనమాట. సైజ్ ఆఫ్ ఎన్ అర్రే ఈజ్ ఈక్వల్స్ టు లోయర్ బౌండ్ మైనస్ అప్పర్ బౌండ్ ప్లస్ 1. ఇప్పుడు 5 అనుకో, లోయర్ బౌండ్ వచ్చేసి 5, అప్పర్ బౌండ్ వచ్చేసి 5, లోయర్ బౌండ్ వచ్చేసి 0 ప్లస్ 1, 6 ఎలిమెంట్స్ స్టోర్ అవుతాయి. కన్సిడర్ ఎన్ అర్రే ఆఫ్ 6:18. దెన్ టోటల్ నెంబర్ ఆఫ్ ఎలిమెంట్స్ ఇన్ ఎన్ అర్రే ఇది ఒకసారి ఇంపార్టెంట్ చూడు. సైజ్ ఆఫ్ ఎన్ అర్రే ఈజ్ ఈక్వల్స్ టు లోయర్ బౌండ్ మైనస్ అప్పర్ బౌండ్ మైనస్ లోయర్ బౌండ్ ప్లస్ 1. 18 minus 6 is 2, 6 plus 1 is equals to 13. Search array. Searching an array means to find a particular element in an array. The search can be used to return the position of an element or check if it exists in the array. అబ్బా, ఇది ఇంపార్టెంట్ రా నాయన, చూసుకో బాగా. లీనియర్ సెర్చ్ టైం కాంప్లెక్సిటీస్ చూడు. లీనియర్ సెర్చ్కి యావరేజ్గా O of n, బెస్ట్ O of 1, వర్స్ట్ O of n. లీనియర్ సెర్చ్ అంటే ఒకదాని తర్వాత ఒకటి వెతుక్కుంటూ పోతావు. యావరేజ్గా ఏంటి, ఎన్ ఉన్నాయి కాబట్టి ఎన్ బై ఎన్ దట్ ఈస్ ఈక్వల్స్ టు ఎన్ లాగానే ఉంటుందిలే. బెస్ట్ ఏంటి అంటే స్టార్టింగ్లోనే తెలుసుకోవచ్చు O of 1. వర్స్ట్ ఏంటంటే లాస్ట్లో తెలుసుకోవచ్చు O of n. బైనరీ సెర్చ్ టైం కాంప్లెక్సిటీ యావరేజ్ అంటే లాగ్ ఆఫ్ ఎన్, అంటే ఎన్ ఉంటే ఎన్ లోపలే తెలిసిపోద్ది. బెస్ట్ ఏంటి అంటే 1. వర్స్ట్ ఏంటి అంటే O of n లాస్ట్లో దొరకడం. బైనరీ సెర్చ్ లాస్ట్లో దొరకడం అన్నట్టు ఉండదు ఉంటుందా. అదే లాగిన్ కదా. బైనరీ సెర్చ్ వర్స్ట్ కేసు O of login, బెస్ట్ O of 1, యావరేజ్ O of login. అదే కదా, తప్పు ఉంది ఇక్కడ. ఇలాంటి కనుక్కోగలుగుతున్నానంటే నాకు టెక్స్ట్ బుక్లో కూడా రాంగ్స్ కనుక్కోగలుగుతున్నానంటే నేను ఇంటెలిజెంట్ గాయ్. పాయింటర్ ఈజ్ అన్ అడ్రస్ ఆఫ్ అన్ అనదర్ వేరియబుల్. ఎగ్జాంపుల్ b ఈజ్ ఈక్వల్స్ టు 10. ఇంట్ స్టార్ అంటే అది పాయింటర్ అనమాట. బి అని అన్నాడు అనుకో. ఇప్పుడు p ఈజ్ ఈక్వల్స్ టు అడ్రస్ ఆఫ్ p అనేది వాడావు అని అంటే అది b యొక్క అడ్రస్ని చూపిస్తుంది. బీలో ఉన్న వాల్యూని కాదు, b ఎక్కడుందో దాని అడ్రస్ని కనుక్కుంటుంది. p అనేది 200 ఉంది, p అనేది 204లో ఉంది. 100 200. 2-dimensional array. The 2-dimensional array can be defined as an array of array. 2D array syntax. Data type array name, row, columns. Representation. అరే నేమ్ ఉంది, దానిలో తర్వాత రో ఉంటుంది, దానిలో కాలమ్స్ ఉంటుంది. 2-dimensional arrays అంటే అట్లా ఉంటుంది. రిప్రజెంటేషన్ ఆఫ్ 2-dimensional arrays అంటే ఒక స్క్వేర్ తీసుకోవాలి. ఫస్ట్ దానిలో ఉండేదానికి లాంగ్ హారిజాంటల్లో ఉండేదాన్ని హారిజాంటల్గా ఉండేదాన్ని ఫస్ట్ రో అనుకోవాలి. తర్వాత సెకండ్ దానిలో ఉండేవన్నీ వర్టికల్ లైన్స్ లాంటివి. Representation of 2D arrays in memory. Row measure order A of I j is equals to B plus I into n plus j into size. If start 0, 0, A of I j is equals to I minus 1 into n plus j minus 1 into size plus base if start 1, 1. Color measure A of I, I j is equals to if I into m plus I into size plus j base. Linked list. A linked list is a linear data structure in which the elements are not sorted at continuous memory location. A linked list is a dynamic data structure. Each element is called a node which has two parts. Info part stores that information and pointer part which point to the next element. ఇన్ఫో ఉంటుంది, పాయింటర్ ఉంటుంది నోడ్లో. దాని తర్వాత స్టార్ట్ ఇన్ఫో పాయింటర్, ఇన్ఫో నల్. ఆపరేషన్ ఆన్ లింక్డ్ లిస్ట్. క్రియేషన్. దిస్ ఆపరేషన్స్ ఆర్ యూజ్డ్ టు క్రియేట్ ఏ లింక్డ్ లిస్ట్ ఇన్ దిస్ నోడ్ ఈస్ క్రియేటెడ్ అండ్ లింక్డ్ టు అనదర్ నోడ్. తర్వాత ఇన్సర్షన్. This operation is used to insert a new node in the linked list. Deletion. In this operation, elements can be deleted at the starting of the list. Transversing. It is a process of going through all the nodes of linked list from one end to another end. Type of linked list. Single linked list. A single linked list is a unidirectional linked list. It is the simplest type of linked list in which every node contains some data and a pointer to the next node of the same data. Start 10, 20, 30 sequential manner. Doubly linked list. A doubly linked list is a bidirectional linked list that contains a pointer to the next as well as the previous node in sequence. Start ఉంది, దాని నుంచి ప్రీవియస్ నోడ్ కనెక్ట్ అయింది, డేటా స్ట్రక్చర్ ప్రీవియస్ డేటా నోడ్ ఈ నోడ్కి కూడా కనెక్ట్ అయింది, తర్వాత ఇది నెక్స్ట్ వచ్చిన నోడ్కి కూడా కనెక్ట్ అయింది, అది దీనికి ఇది దానికి కూడా కనెక్ట్ అయింది. సో లాస్ట్ వరకు ఇలా జరుగుతుంది. ఇది డబుల్ లింక్డ్ లిస్ట్. Circular linked list is circular linked list is that in the which the last node contains a pointer to the first node of the list. ఇప్పుడు 10 ఉంది, 20 కనెక్ట్ అయింది, 20 30 కనెక్ట్ అయింది, 30 మళ్ళీ వచ్చి 10కి కనెక్ట్ అయింది. స్టార్ట్ కూడా 10 దగ్గర నుంచే స్టార్ట్ అవుతుంది. ఇది సర్కిల్ లింక్ లిస్ట్. సర్కిల్ డబుల్లీ లింక్డ్ లిస్ట్ ఈజ్ అ సర్క్యులర్లీ డబుల్ లింక్డ్ లిస్ట్ విత్ ద మిక్చర్ ఆఫ్ డబుల్ లింక్డ్ లిస్ట్ అండ్ ఏ సర్కిల్ లింక్డ్ లిస్ట్. ఇప్పుడు 10 20తో కనెక్ట్ అయింది, 20 10తో కూడా కనెక్ట్ అయింది, 20 30తో కనెక్ట్ అయింది, 30 20తో కూడా కనెక్ట్ అయింది, 30 మళ్ళీ వెళ్ళి 10తో కనెక్ట్ అయింది, 10 వెళ్ళి 30తో కూడా కనెక్ట్ అయింది. ఇది సర్క్యులర్లీ డబుల్ లింక్డ్ లిస్ట్. తర్వాత representation of linked list. A data item, an address of another node. We wrap both the data item and the next reference in the struct as syntax struct node in data struct node into next. Linked list applications. Dynamically memory allocation implemented in stack and queue in undo functionalities of the software, hash tables, graphs. Stacks. Stack is a non-primitive linear data structure. It is an order list in which the addition of new data item and deletion of already existing data item is done from only one end is known as the top of the stack. TOS. పాప్ బయటికి దానిలో నుంచి ఎలిమెంట్ బయటికి తీయడం, పుష్ దానిలోకి ఎలిమెంట్ పెట్టడం అన్నీ టాప్లోనే జరుగుతాయి. కింద నుంచి ఆర్డర్ స్టార్ట్ అవుతుంది 0 1 2 3 4 అని. It flows the LIFO last in first out pattern, which means the last added element will be the first to be removed from the stack. Stack has two operations: push operation, pop operation. Push operation. Every push operation top is incremented by 1. Top is equals to top plus 1. In case of an array is full, no new element is added. This condition is called stack or full stack overflow condition. The process of adding a new element of the top of the stack is called push operation. Pop operation. The process of deleting an element from the top of the stack is called pop. Every pop operation the stack top is decremented by 1. Decreased by 1. Top is equals to top minus 1. This is called operational stack underflow. ఇప్పుడు ఇక్కడ 10 20 30 ఉంది, 30 బయటకు వెళ్తే ఇది పాప్ ఆపరేషన్. టాప్ 2లో పాప్ ఆపరేషన్ జరిగిందనమాట. 30 డిలీటెడ్. టాప్ ఈజ్ ఈక్వల్స్ టు టాప్ మైనస్ 1. 2 మైనస్ 1 ఈజ్ ఈక్వల్స్ టు 1 అనమాట. న్యూ టాప్ వచ్చేసి 1. Stack notation. There are 3 stack notation. Infix notation, where the operation is written between the operands. Example a plus b plus operator ab operands. ఓకే, ప్లస్ అనేది ఆపరేటర్. సింబల్స్ వచ్చేసి ఆపరేటర్స్. తర్వాత వాల్యూస్ వచ్చేసి ఆపరాండ్స్. ప్రిఫిక్స్ నోటేషన్. దిస్ ఈజ్ ద ఆపరేషన్ ఈజ్ రిటర్న్ బిఫోర్ ద ఆపరాండ్. ఇట్ ఈజ్ ఆల్సో నోన్ యాజ్ అ పాలిష్ నోటేషన్. ఎగ్జాంపుల్ ప్లస్ ఏబి. ప్రిఫిక్స్ అంటే ప్రిఫిక్స్ ముందే వస్తుంది సింబల్, ప్లస్ వచ్చి ఏబి అని వస్తుంది. ఒక సింబల్ కనపడితే దాని తర్వాత కనపడే 2 ఆపరాండ్స్ మధ్యలో ఆ సింబల్ పెట్టి ఆపరేషన్ పర్ఫామ్ చేయాలి. పోస్ట్ ఫిక్స్ అంటే రెండు ఆపరాండ్ ఒక సింబల్ కనపడితే దానికి ముందుండే 2 ఆపరాండ్స్ మధ్యలో అది సింబల్ పెట్టి ఆపరేషన్ చేయాలి. పోస్ట్ ఫిక్స్ ఈజ్ అన్ ఆపరేటర్ ఇన్ విచ్ రిటర్న్ ఆఫ్టర్ ద ఆపరాండ్స్. ఇట్ ఈస్ ఆల్సో నోన్ యాజ్ ద సఫిక్స్. పోలిష్ నోటేషన్. The postfix suffix Polish. Convert the following infix to prefix and postfix. For a plus b into star the multiplication c divided by d, c divided by t plus e XOR f by z ప్రిఫిక్స్ ఉందా, దీన్ని ప్రిఫిక్స్ లెక్క మార్చాలి అంటే ఇప్పుడు ప్లస్ ముందు ఇది ప్లస్ ఏ ఇంటూ బి తర్వాత స్టార్ సి గ్రాఫ్ డి ప్లస్ ఈ ఆఫ్ ఎఫ్ సి ఆఫ్ సి లెట్ ఏ ప్లస్ బి ఈజ్ ఈక్వల్స్ టు R1 సిడి ప్లస్ ఈ పవర్ ఎఫ్ ప్లస్ జీ లెట్ ఈఎఫ్ ఈజ్ ఈక్వల్స్ టు R2. ఈఎఫ్ వచ్చేసి R2 అనమాట. దాని తర్వాత సిడిని R3 చేశాడు. R1 into R3 plus R2 by Z. Let R2 into Z is equals to R4. Okay. Let into R1 into R1 into R1 R3 is equals to R5. R5 plus R4 plus R5 R4. Now enter the values of R5 R4 R3 R2 R1 plus into R1 into R3 divided by R2 into Z. ప్లస్ ఇంటూ ప్లస్ ఏబి బై సిడి బై ఏఈఎఫ్జి. ఇదే పోస్ట్ఫిక్ని ఎలా చేయాలో ఒక సెకండ్ ఆగి ఇది నువ్వే చూడు, ఇది చెప్తే అర్థమయ్యేది కాదు. ఇక్కడ ఏ ప్లస్ బి ఇంటూ సిడి సి డివైడెడ్ బై డి ప్లస్ ఈ అండ్ ఈఆర్ ఎఫ్ ఈవెన్ జీ ఉంది. ఇప్పుడు సింబల్ ఏబి తర్వాత వచ్చింది, ప్లస్ ఏబి ప్లస్ వచ్చేసి ఆర్ అనుకోవాలి. దాని తర్వాత ఈఎఫ్ కొలింది, ఈఎఫ్ పవర్ ఎఫ్ వచ్చేసి ఈఎఫ్ పవర్ వచ్చేసి R2. ఇక్కడ R1 ఇంటూ సి గివెన్ బై టీ ప్లస్ R2 బై జీ ఉంది. సిడి డివైడింగ్ లైన్ వచ్చేసి R3 అనుకున్నాడు. R2 ఇంటూ జీ బై సి డివైడెడ్ వచ్చేసి R4 అనుకున్నారు. R5 ప్లస్ R4 అనుకున్నారు. సో ఇది ఇలా ఉంటుంది. ఇవి స్టాక్తోనే ఉన్న ఆపరేషన్స్ కాబట్టి స్టాక్స్ నుంచి నేర్చుకున్నప్పుడు పోస్ట్ ఫిక్స్ ఇన్ఫిక్స్ ఈ ఈక్వేషన్స్ని పోస్ట్ ఫిక్స్ ఎక్స్ప్రెషన్ లాగా ప్రిఫిక్స్ ఎక్స్ప్రెషన్ లాగా కూడా కనుక్కోవాలి. తర్వాత Q is a non-primitive linear data structure. The first added element will be the first to be removed from the queue. That is the reason Q is called FIFO type list. First in, first out. Last in, first out. Yeah. In Q, every insertion operation rare is incremented by 1. R is equals to R plus 1 and every deletion operation front is incremented by 1. F is equals to minus 1 and F is equals to F plus 1. Q ఉంది 0 1 2 3 empty Q. F is equals to 0, R is equals to 0, insert is 10. 0 ప్లేస్లో 10 వస్తుంది, ఫ్రంట్ రేర్. ఇన్సర్ట్ వచ్చేసి 20. F is equals to 0, R is equals to 1. 0 పొజిషన్లో 10, I పొజిషన్లో 20. F తర్వాత R ఇక్కడికి వస్తుంది. బేసిక్ ఆపరేషన్ ఆఫ్ Q. NQ. Add an element to the end of the queue. DQ. Remove an element from the front of the queue. Is empty. Check if the queue is empty. Is full. Check if the queue is full. Peek. Get the value of the front of the queue without removing it. Application of queue. CPU scheduling, disk scheduling. Handling of interrupts in a real-time system. Call center phone system using queues to hold people, calling them in order. Unlike stack, queue is also considered as an ordered list of the data, the order list of the data that has a similar data type. Priority queue. Priority queue is an extension of the queue with the following properties. An element with the high priority is dequeued before an element with a no priority. ప్రయారిటీ క్యూలో ఏంటంటే క్యూలో పెట్టేవాడికి ప్రయారిటీ ఇస్తారు. ప్రయారిటీ ఉండే వాటిని ముందు కంప్లీట్ చేసి ప్రయారిటీ లేని వాటిని లేట్గా కంప్లీట్ చేస్తారు. ప్రయారిటీ ఉండేవి ప్రయారిటీ లేని వాటికన్నా ఫస్ట్ అయిపోతాయి. ఆపరేషన్ ఇన్సర్ట్ ఐటమ్ ప్రియారిటీ insert an item with the given priority time O of log n. తర్వాత get highest priority returns the highest priority item. Operation implemented by the linear searching the highest priority item in array O of 1. Delete highest priority removes the highest priority. Operation can be implemented by first linearly searching an item, then removing the item by moving all subsequent items one position back. Time of O of log n. Heap అనమాట. Heap is generally preferred for an priority queue implemented because heaps provide better performance compared array or linked list. హీప్ వచ్చేసి అరే ఆర్ లింక్డ్ లిస్ట్ కన్నా మంచి పర్ఫార్మెన్స్ ఇస్తుంది. Circular queue. A circular queue is one in which the insertion of a new element is done at very first location of queue is full. ఇప్పుడు క్యూ ఉంది, Q0 ఉంది, తర్వాత Q1 F is equals to R is equals to -1, Q2 Q3 Q4 అన్ని సర్క్యులర్గా ఉన్నాయి. ఏ సర్క్యులర్ క్యూ ఓవర్కమ్ ద ప్రాబ్లమ్ ఆఫ్ యూటిలైజింగ్ స్పేస్ ఇన్ ఏ లీనియర్ క్యూస్ ఇంప్లిమెంటెడ్ యాజ్ అరే. తర్వాత బైనరీ ట్రీ. బైనరీ ట్రీ ఈజ్ ఎ ఫైనైట్ సెట్ ఆఫ్ డేటా ఐటమ్ విచ్ ఈజ్ హీప్ గురించి మళ్ళీ ఎక్కడైనా చెప్పాడా? హీప్ గురించి సరిగ్గా చెప్పలా వీడు ఇక్కడ. ఒక సెకండ్ హీప్ గురించి చూసి చెప్పాడు. హీప్ అంటే ఇట్లా ముందరేసిన ఒక కుప్పలాగా. మిన్ హీప్, మ్యాక్స్ హీప్. మ్యాక్స్ హీప్ అంటే 100 అన్నిటికన్నా హైయెస్ట్ ఎలిమెంట్ నుంచి స్టార్ట్ అవుతుంది. మిన్ హీప్ అంటే అన్నిటికన్నా లోయెస్ట్ ఎలిమెంట్ నుంచి స్టార్ట్ అవుతుంది.
Get dairy, bread, eggs, and...
Hi, I'm Gail Locke-McDowell, author of Crack and Coding Interview. Today we're going to talk about a topic that a lot of candidates forget about, heaps. Smaller than their children. So the root node will be the very smallest element, and then looking down the tree, down the heap, the elements get bigger and bigger and bigger. So that's the basics of what a heap is, but how do we actually create and maintain such a data structure? So let's start with just insertion. So we insert an element, it always goes in the next empty spot, looking top to bottom, left to right. So we go first we insert an element here, and then here, and then here, and then here, and so on through the tree, through the heap. So that's how insertion works, but then of course what happens if that's not really where the element should go? Well, what we can do is we can insert the element there, and then bubble it up until we get to the right spot. So we take the inserted element, we compare it with its parent. If it's out of order, swap them, and then keep going up the tree in this process. Now what about removing the minimum element? So we know the minimum element will always be the root node, and so that's easy to find, but then if we want to remove it, we might have an empty spot. So what we do here is we remove the min element there, so we take out the root, and then we swap that value of the root with the last element added. And then, of course, that element might not be at the right spot, so we take the root element and bubble it down to the next spot. So we compare the root with its children, its left child, its right child, and then swap it with the smaller of the two. And then we keep going down the tree until the heap property is restored. So that's how a tree operates. Let's think about how a heap operates. Let's talk about implementation now. So implementation is kind of interesting. You might have assumed that we implemented as a simple class node with a left node and a right node, and certainly we could do it that way. But there's even better way of implementing it. Note that when we add elements to the heap, they're always getting added in a very particular spot. There aren't going to be any gaps in the heap. So we have the 0th element here, and then the 1st, 2nd, 3rd, 4th, etc. And so that means that we can actually use an array instead to store these values, and that makes it very compact. And a simple equation can map from an index to its left child, its right child, or to its parent. And so we can still get to the left and right child, but we don't need to have this overhead of a node class. So now that we've covered the basics of what a heap is, let's turn to the actual code for this. We'll implement a min heap with a simple class that wraps this items array. This is going to be an array of a fixed length, but if it gets too big, we'll increase the capacity. Now I'm going to get a little bit of a head start and cheat a little bit by just adding in a whole bunch of simple helper methods. So these are just simple methods that get the left and right child or the parent index, actually check if they exist, or actually get the values themselves. So I'm just getting a little bit of a head start here. And I'll get another little bit of a head start by adding in 2 extra methods here. One is a swap method that swaps the values of 2 indices, and another one is an ensure extra capacity method. Now this does is it checks if the array is full, and if so, it creates a new array of double that size, and it copies all the elements over. And this, by the way, is the basics of how an array list operates. Now let's turn to the real code. The first method I'll implement is a peek method, and this first it checks if the array is empty. If so, returns an exception because there's nothing at the front. Otherwise, it just returns the first element in the array, which will always be the minimum element and essentially the root of the heap. This method we'll do is a pull method. Now what this does is actually extract the minimum element and it actually removes it from the array. So first we'll check if the array is empty. If so, throw an exception. Otherwise, I need to actually get the value. So item is items of 0. Then I need to take the very last element in the array and move it into the very first element. Then I need to shrink my array, or shrink essentially the size of it. And then I need to go and actually re-heapify. So I removed the root element, so I need to heapify down. And I'll go fill this method in shortly. So in this case, if we remove the 10, the minimum element, it's going to get deleted. Then the 17 is going to get moved up to where the 10 is. So see in the array, that's like this. So the 17 gets put in here. And then we go and adjust the heap to shift elements down as needed. My next method is going to actually add an element in here. So first thing I want to do is I want to make sure there is capacity. So I'll call my ensure extra capacity method. Then I'm going to add my element into the very last spot. So items of size equals this new item. Then increase my size. And then I need to actually heapify up. So I need to fix the heap looking upwards, swapping each element with its parent as necessary. So in this case, if we wanted to add an element, say 8, we'd add it at the very last element, and then we'd go and adjust our heap, moving things up as necessary. Now for the real fun, I need to actually implement these heapify methods. So heapify up is going to start with the very last element added, which is at size -1, and then it's going to walk up as long as there's a parent item, and as long as essentially I'm out of order. So as long as my parent item is bigger than me, then hey, things are out of order. So swap my parent index, swap my value with my parent, and then walk upwards. So let's walk through this on the 8 that was inserted. So what we do here is we'll compare 8 to this 15. It's out of order, so we'll need to swap those values. So 15 goes down here and 8 goes up here. Or on the array, it'll look like this. Then we compare this 8 to the 10, and then that's still out of order. And so we'll go and move the 10 down and swap the 8 up there. And now we've returned to the heap properties. We have 8 at the top, 10 and 20 below it, then 17 and 15 below that. Heapify down is a little bit more complicated, but it's still quite manageable. First, we're going to start off with our root element, which is at index 0. And then we're going to say, well, as long as I have children, keep walking down and trying to fix up my heap. Now I only need to check if there's a left child, because if there's no left child, then there's certainly no right child. Then I'm going to set this smaller child index equal to the smaller of the left and the right child. So I'm going to take a guess with set it equal to the left child. And then I'm going to say, hey, if there's a right child and my right child is even smaller than my left child, smaller child index should equal my right child. Now what I'm going to say, remember I'm looking downwards on the heap. So now what I'm going to say is, hey, if items of index, if I'm smaller than the smaller of my 2 children, then everything's good and everything's back in order here and I can just exit. If that's not the case, then our heap is still out of order, and then I need to swap my value with my smaller child, and then move down to my smaller child. I'll just actually move this out here. All right, so that's the basics of how heapify down works. Let's walk through this on an example. I'll make this example slightly larger. So if we do an extract min such that 10 gets removed, then we remove 10, we replace it with 25. I'll do it on the array too so you can see what's going on there. Then we compare 25, the root, and replace it with the smaller of its left and right child. So we swap the 25 and the 15. So 25 comes down here, 15 comes up there, and we can do it down here too. So 15 goes here, 25 goes here. Then we compare 25 to 17. It's still out of order since 25 is bigger than 17. So we do 17 comes up here, we swap those, and 25 goes down here. So now we have a heap again that looks like 15, 17, 20, and 25. And as you can see, our min heap property has been restored. So now that you understand what a heap is and how it works, why don't you try out using a heap on a new problem? Good luck.
Okay, binary tree. Binary tree is a finite set of data item which is either empty of consisting of a single item called root and two disjoint binary tree called the left subtree and right subtree. The binary tree, every node can have maximum of two children which are known as the left child and right child. ఇప్పుడు ఇది రూట్ లెఫ్ట్ సబ్ ట్రీస్ ఉంటాయి, బి ఉంది, తర్వాత ఇది రైట్ సబ్ ట్రీ సిఈఎఫ్ ఉంది. టైప్స్ ఆఫ్ బైనరీ ట్రీ. ఫుల్ బైనరీ ట్రీ అంటే ఏ బైనరీ ట్రీ ఈజ్ ఫుల్ ఇఫ్ ఎవ్రీ నోడ్ హ్యాస్ 0 or 2 చైల్డ్స్. ఇది ఫుల్ బైనరీ ట్రీ కాదు. ఎవ్రీ నోడ్కి లైక్ 0 అయినా ఉండాలి, ఓకే ఇది ఫుల్ బైనరీ ట్రీ. ఎవ్రీ నోడ్కి అయితే 0 ఉంది, సికి 0 ఉన్నాయి, బికి 2 ఉన్నాయి, డికి 0 ఉంది, ఈకి 0 ఉంది, ఏకి 2 ఉన్నాయి. సో ఇది ఫుల్ బైనరీ ట్రీనే, గుర్తుపెట్టుకో. తర్వాత కంప్లీట్ బైనరీ ట్రీ. ఏ బైనరీ ట్రీ ఈజ్ కంప్లీట్ బైనరీ ట్రీ ఇఫ్ ఆల్ లెవెల్స్ ఆర్ కంప్లీట్లీ ఫిల్డ్. ఎగ్జాంపుల్ లెవెల్ 0, 2 power 0. Complete binary tree. A binary tree is complete binary tree if all levels are completely filled. A ఉంది లెవెల్ 0, 2 power 2 degrees equals to 1. ఇది B ఉంది, C ఉంది, లెవెల్ 1, 2 power 1 is equals to 2 అంటే 2 నోట్స్ ఉన్నాయి. ఓకే, అది లెవెల్ 0, 2 power 0 is equals to 1. ఇది లెవెల్ 1, 2 power 1 is equals to 2. తర్వాత ఇది లెవెల్ 2, 2 power 2 is equals to 4. DEFG ఉన్నాయి. ఇది లెవెల్ 3, 2 power 3 is equals to 8. 8 ఉండాల్సిన చోట 4 ఉన్నాయి. A perfect binary tree is a tree with all internal nodes has 2 children and all levels are at the same level which are all has 2 power n child. ఓకే, అంటే డౌన్ లాస్ట్ లెవెల్లో తప్పితే మిగతా అన్నిట్లో సేమ్ నెంబర్ ఉంటే అది పర్ఫెక్ట్. కంప్లీట్ అంటే ఏంది, ఉన్న లైక్ ఇఫ్ ఆల్ లెవెల్స్ ఆర్ కంప్లీట్లీ ఫిల్డ్. ఇక్కడ ఈఎఫ్ఎఫ్జి కంప్లీట్గా ఫిల్ అవ్వక్కర్లేదు. ఇక్కడ పర్ఫెక్ట్ బైనరీ ట్రీ ఉంది. ఏ వచ్చేది బిసి, పిఈఎఫ్జి. A perfect binary tree, a tree in which all internal nodes has 2 children and all leaves are at the same level in which all level has 2 power n children. Pre-order traveler, NLR, node left right. In order traveler, LNT, left node right. Post order traveler, LRN, left right node. నేను ఇది మన ఛానల్లో ఒకటి వీడియో ఉంది, లైక్ ప్రీ అంటే ముందర ఒక ఆరో మార్క్ వేసుకొని వీటన్నిటి అన్ని నోట్స్ దగ్గర ఒక లైన్ గీసి ఫస్ట్ ఆరో మార్క్ దేని టచ్ అవుతుందో అది ప్రీ ఆర్డర్. ఇన్ ఆర్డర్ అంటే లైన్ కిందకి గీసుకొని అన్నిటికి ఒక గీత గీసి ఏదైతే ఫస్ట్ లైన్ టచ్ చేస్తుందో అలా. పోస్ట్ అంటే ఒక ఆరో మార్క్ అన్ని నోట్స్కి వెనకాల గీసి ఒక లైన్ గీసి ఆ లైన్ ఏది ఫస్ట్ ఎట్లా టచ్ అవుతుందో అలా. కానీ ఇలా ఉండాలి. ప్రీ ఆర్డర్ అంటే నోడు లెఫ్ట్ రైట్, ఇన్ ఆర్డర్ అంటే లెఫ్ట్ నోడు రైట్, పోస్ట్ ఆర్డర్ అంటే లెఫ్ట్ రైట్ నోడ్. LNR ఎల్ఎన్ఆర్ ఉండాల్సింది, ఇక్కడ సెకండ్లో ఎల్ఎన్టీ అని ఉంది, ఆర్ ఉండాలి అక్కడ. ఎన్ఎల్ఆర్, ఎల్ఎన్ఆర్, ఎల్ఆర్ఎన్. ఇప్పుడు ఏబీసీ ఉంది. వీటన్నిటికీ ముందర గీత గీసామనుకో, ఏకి ముందర ఒక గీత, బీకి ముందర ఒక గీత, సికి ముందర ఒక గీత. ప్రీ ఆర్డర్ అనుకో, ఏ నుంచి స్టార్ట్ అవ్వాలి, ముందు అక్కడ నుంచి ఇలా గీత వచ్చి ఇలా వెళ్తే ఫస్ట్ ఏ, తర్వాత బి, తర్వాత సి. ఇన్ ఆర్డర్ అనుకో, అన్నిటికీ కింద గీత గీయాలి. తర్వాత ఇలాగ గీత గీస్తుంటే ఫస్ట్ బి తగిలి, తర్వాత ఏ తగిలి, తర్వాత సి తగులుద్ది. సో బిఏసి. తర్వాత పోస్ట్ ఆర్డర్ అంటే అన్నిటికీ వెనకాల గీత గీయాలి. ఫస్ట్ బీకి తగిలి, తర్వాత ఏకి తగిలి, తర్వాత సికి తగిలి, తర్వాత సికి తగిలి, తర్వాత ఏకి తగులుద్ది. BCA. B tree. B tree is a self-balancing tree in the most of the other self-balancing trees like AVL and red black tree. It assumes that everything is the main memory. Time complexity of B tree. Sorting algorithms O of log, search కి వచ్చేసి O of login, ఇన్సర్ట్కి వచ్చేసి O of login, డిలీట్కి వచ్చేసి O of login. సో బీ ట్రీలో సర్చ్, ఇన్సర్ట్, డిలీట్ మూడిటికి O of login టైమే పడుద్ది. ప్రాపర్టీస్ ఆఫ్ బీ ట్రీ. ఆల్ నోట్స్ ఆఫ్ ద లీఫ్ మస్ట్ బీ ఆన్ ద సేమ్ లెవెల్. అట్లీస్ట్ 2 రూట్ నోట్స్ ఆర్ రిక్వైర్డ్. 2 రూట్ నోట్స్ అయినా ఉండాలన్నమాట. ఈచ్ బీ ట్రీ నోడ్ ఏ maximum of m children. Each node in a B tree includes at least m/2 children, except the root and leaf node. Maintain sorted data. Minimum characters is leaf is equals to 0, root is equals to 2. 2 roots అని ఉండాలి. ఇంటర్నల్ నోడ్స్ ఎన్ని ఉంటాయంటే m/2. ఎవ్రీ నోడ్ హ్యాస్ మ్యాక్స్ m-1 keys. Mean key is equals to root node 1. All other keys is equals to m/2 minus 1. M అంటే ఆర్డర్ ఆఫ్ ట్రీ. తర్వాత గ్రాఫ్ is a data structure that are not linear data structure made up of infinite numbers of vertices and the edges that connect them. Graph in data structures are used to address real problem in which it represents the real problem in which it represents the problem of area as a network like telephone network, circuit network and social network. 1 ఉంది, 2, 3 ఉంది. 2కి 5 కనెక్ట్ అయింది, 3కి 5 కనెక్ట్ అయింది, 3కి 1 కూడా కనెక్ట్ అయింది, అండ్ 2కి 4 కనెక్ట్ అయింది, 4కి 5 కనెక్ట్ అయింది. 2, 4, 1, 3, 5 అని నోట్స్. ఈ కనెక్షన్ వచ్చేసి ఎడ్జెస్. దిస్ గ్రాఫ్ ఈజ్ అ సెట్ ఆఫ్ వర్టిసెస్. V ఈజ్ ఈక్వల్స్ టు 1, 2, 3, 4, 5 అండ్ ద సెట్ ఆఫ్ ఎడ్జెస్ వచ్చేసి, ఎడ్జెస్ ఏమేమి ఉన్నాయి, 1 నుంచి Tకి ఉంది, 1 నుంచి 3కి ఉంది, 2 నుంచి 3కి ఉంది, 2 నుంచి 5కి ఉంది, 2 నుంచి 4కి ఉంది, అండ్ 5 నుంచి 2కి ఉంది, అండ్ 3 నుంచి 5కి ఉంది, అండ్ 4 నుంచి 5కి ఉంది. ఆపరేషన్ ఆఫ్ graph in data structure. Creating graphs, insert vertex, delete vertex, insert edge, delete edge. ఇవి ఆపరేషన్స్ యొక్క గ్రాఫ్ డేటా స్ట్రక్చర్లో మనం పర్ఫామ్ చేసేది. గ్రాఫ్ ట్రావర్సల్ ఆల్గోరిథం. Graph traversal is a subset of tree traversal. There are 2 techniques to implement a graph traversal algorithm: breadth first search or BFS, depth first search or DFS. Breadth first search, 2 data structures of traversing the graph. Visited array size of the graph. Queue data structure using FIFO concept until the queue is not empty and no vertex is left to be visited. ఫస్ట్ 1 ఉంది, 1 నుంచి 2 కనుక్కున్నాం, 2 తర్వాత 3. బ్రెత్ అంటే వెడల్పుగా ఉండే ఫస్ట్ అయిపోతుంది. తర్వాత 2 నుంచి 3కి వెళ్ళాం, 2 నుంచి 4కి వెళ్ళాం, 4 నుంచి 5కి వెళ్ళాం, తర్వాత 3 నుంచి 6కి వెళ్ళాం. సో బిఎఫ్ఎస్లో 1, 2, 3, 4, 5, 6 వస్తుంది అనమాట పాత్. తర్వాత డిఎఫ్ఎస్, డెప్త్ ఫస్ట్ సెర్చ్. DFS is an algorithm. The DFS algorithm or explores data structures such as trees and graphs. The DFS algorithms begins at the root nodes and examines each branch as feasible possible before backtracking. Examine any two data structures for traversing the graph. Visited array, the size of the graph, stack data structure. Using the FIFO principle, stack data structure is not empty. 1 నుంచి 2కి 2 నుంచి 3కి ఈ ఫస్ట్ ఏది వచ్చిందో దాన్ని కంప్లీట్గా కౌంట్ చేస్తాం. తర్వాత 1 ఉంది, 1 నుంచి 2కి వెళ్తాం, 2 నుంచి 4కి వెళ్తాం, 4 నుంచి 5కి వెళ్తాం, తర్వాత 1 నుంచి 3కి వెళ్తాం. అదే 5కి వచ్చిన తర్వాత 3కి వెళ్తాం అండ్ 3 నుంచి 6కి వెళ్తాం. ఓకే, ఈ డయాగ్రామ్ బాగా గుర్తుపెట్టుకోండి, ఇంకా చాలా బాగా అర్థమవుతుంది. అప్లికేషన్ ఆఫ్ గ్రాఫ్. ఫ్రెండ్స్ సజెస్టింగ్ ద system of on Facebook is based on graph theory. Graph transformation system manipulate graph in memory using rules. Graph database stores and queue graphs structure data in a transaction safe permanent manner. Difference between stack and queue. Stack ki queue ki difference ఏంటి? Stack the collection of elements in the last in first out. The queue అంటే the collection of elements in first out. ఇది LIFO, ఇది FIFO. Objects are inserted and removed at the same time, called top of the stacks. Objects are inserted and removed from different ends, called front and rear end. Insert operation is called push operation. Insert operation is called NQ operation. Delete operation is called as pop operation. Delete operation is called DQ operation. In stack there is no wastage of memory space. In queue there is a wastage of memory space. Plate counter at marriage reception is an example of stack. Pure desi example. Students studying in the line of fees counter is an example of queue. లీనియర్ డేటా స్ట్రక్చర్, లీనియర్ డేటా స్ట్రక్చర్స్కి డిఫరెన్సెస్ ఏంటంటే, ఇప్పుడు నాన్ లీనియర్ డేటా స్ట్రక్చర్డ్ ఆర్ కంపారిటివ్లీ డిఫికల్ట్ ఇంప్లిమెంటెడ్ అండ్ అండర్స్టాండింగ్ యాజ్ కంపేర్డ్ యాజ్. ఇవి అర్థం చేసుకోవడం కానీ ఇంప్లిమెంట్ చేయడం కానీ లీనియర్ డేటా స్ట్రక్చర్స్ కన్నా కష్టం. లీనియర్ డేటా స్ట్రక్చర్స్ ఆర్ కాంప్లెక్స్, కంపారిటివ్లీ ఈజీ టు ఇంప్లిమెంట్. ఎగ్జామ్లో రాయడానికి పనికొస్తాయి. The data element connect to each other hierarchically. The data element connect to each other sequentially. It is not easy to traverse in multiple runs. It can traverse in a single run. In a memory friendly, it is not very memory friendly. Map, graph, tree, list, array, stack, queue. Array ki linked list ki differences. Array is a collection of homogeneous same data types. Linked list is a collection of node data and addresses. Size of an array is fixed. Size of an list is not fixed. Memory is allocated from the stacks. Memory is allocated from the heap. Work with static data structures. Work with dynamic data structures. Array elements are independent to each other. Linked list elements are dependent to each other. Array takes more time, insert and deletion. Linked list take less time, insertion and deletion. Tree ki graph ki differences. Tree, there is a unique node called root in the tree. Graph, there is no unique node. Tree is a collection of nodes and edges. Node, T of nodes and edges. Graph is a collection of vertices, nodes and edges. Graph is equals to edges, vertices and edges. ఇక్కడ నోడ్ ఎడ్జెస్, ఇక్కడ వర్టిసెస్ ఎడ్జెస్. అక్కడ నోడ్ అనేది ఈ రూట్లో ఉంటుంది, రూట్. ఇక్కడ అలా యూనిక్ అనేది ఏం లేదు స్టార్టింగ్ పాయింట్ లాగా. there will not be any cycles or loops. There can be cycles or loops. It is a pre-order, in order and post-order traversal. It is breadth first search and depth first search traversal. Heap data structure. Heap is a special tree-based data structures in which the tree is complete binary tree. A on the B, C, D, E, F, G. A, B, C, D, E, F, G, 1, 2, 3, 4, 5, 6, 7. Formula. If node is at the index of I, in the left shade is at 2 into I, the right side is at 2 into I plus 1. Its parent is at I by 2. This is true when your heap is starting from index 1. If you represent a binary tree in an array, then there should not be any empty locations or gaps in between the element pins from the first element to last element is element in between anywhere. Height of a complete binary tree will be minimum only, that is log n. Heap, మ్యాక్స్ హీప్ మిన్ హీప్. మ్యాక్స్ హీప్లో ఫస్ట్ 50 ఉంది, కిందికి వెళ్ళే కొద్దీ ఇంకా తగ్గుతూ ఉంటుంది, 30 20 15 10 8 16. మిన్ హీప్లో స్టార్టింగ్ స్మాల్ ఉంటుంది, పోయే కొద్దీ పెరుగుతుంటాయి, 30 25 35 40 32 25 25 అంటే కరెక్ట్ వచ్చు. మ్యాక్స్ హీప్. A max heap is a complete binary tree in which the value in each internal node is greater than or equal to the values in the children of the node. Max heap data structure is useful for sorting data using heap sort. 50 is greater than 30, 20. 30 is greater than 15, 10. 20 is greater than 8, 16. Min heap. A min heap is a heap where every single parent node, including the root, is less than or equals to the value of its children nodes. The most important property of a min heap is that the node with the smallest or minimum value will always be the root node. 10 is less than 30, 20. 30 is less than 35, 40. 20 is less than 35, 25. Operations of heap. Heapify. A process of creating a heap from an array. Then heapify enter. Is it fun fact? అరే నుంచి హీప్ని తయారు చేయడాన్ని హీపిఫై అంటారు. హీపిఫై. Insertion. Time complexity of heap is O of log n. Deletion time complexity O of log n. Peek. To check to find the most superior element in the heap. Hashing. Hashing is a technique or process of mapping keys and values into the hash table. By using a hash function, it is done for fastest access to elements. Hashing. Store and retrieving data in O of one time. Search key 24 52 91 67 48 83. Hash table. Hash function k mod 10 k mod n mid square folding method. K mod n is equals to n minus 1 0. 24 mod 10 is equals to 4. సో అది ఫోర్త్ ప్లేస్లోకి వెళ్ళాలి. మొత్తం 10 ఉంది కాబట్టి సైజు, కాబట్టి k డివైడెడ్ బై 10, డేటా వచ్చేసి డివైడెడ్ బై 10. 52 మొత్తం 10 సెల్స్ ఉన్నాయి కాబట్టి డివైడెడ్ బై 10 2 వస్తుంది. సో 52 వచ్చేసి 2 ప్లేస్లోకి వెళ్తుంది. 91 డివైడెడ్ బై 10 1 వస్తుంది. సో 91 ఫస్ట్ ప్లేస్లోకి వెళ్తుంది. అండ్ 67 డివైడెడ్ బై 10 7 వస్తుంది. సో 7th ప్లేస్లోకి వెళ్తుంది. 48 డివైడెడ్ బై 10 8th ప్లేసెస్లోకి వెళ్తుంది. 43 డివైడెడ్ బై 10 3 థర్డ్ ప్లేస్లోకి వెళ్తుంది. Collision in data in using collision in hashing or collision resolution techniques. Chaining, open hashing, open addressing, closed hashing. Closed hashing అంటే linear, quadratic, double hashing. B tree and B plus tree. B tree వచ్చేస్తే data is stored in a leaf as well as internal nodes. B plus tree అంటే data is stored only in the leaf nodes. Leaf nodes not linked together like linked list. Search is slower deletion complex. Search is faster deletion easy directly from leaf node. ఇక్కడ బీపీ కీ బీడీపీ బీపీ కీ డీపీ బీపీ సో ఆన్. బీపీ వచ్చేసి నాకు బీపీ మీన్స్ బ్లాక్ పాయింటర్, డీపీ అంటే డిజిటల్ పాయింటర్. ఇక్కడ బీపీ ఉంది, తర్వాత కీ ఉంది, తర్వాత బీపీ, తర్వాత కీ, తర్వాత బీపీ, తర్వాత కీ, తర్వాత బీపీ. ఫస్ట్ బీపీ అంటే బ్లాక్ పాయింటర్, కీ తర్వాత డేటా పాయింటర్, తర్వాత కీ డేటా పాయింటర్ అండ్ సో ఆన్. ఇది బీ ప్లస్ ట్రీలో, బీ ట్రీలో. బీ అంటే బ్లాక్ పాయింటర్ ట్రీ, బైనరీ ట్రీ అనుకునే తట్టు కూడా ఉంది. Algorithm. Analysis of algorithms as well as defined procedure to solve a specific problems is called algorithm. Data structure plus algorithm is equals to programming. Algorithms criteria వచ్చేసి ఇన్పుట్ నుంచి అవుట్పుట్ టు ఫిట్నెస్ టు డెఫినెట్నెస్ నుంచి ఎఫెక్టివ్నెస్. తర్వాత అసిమ్నోటిక్ నొటేషన్స్. ఇవి ఇక్కడి నుంచి బాగా ఇంట్రెస్టింగ్గా వెళ్తుంది టాపిక్. అసిమెట్రిక్ నోటేషన్స్ ఓకే. ఇక్కడ నుంచి రై అని వెళ్తుంది. 1 అవర్ అయిపోయింది ఆల్మోస్ట్. పార్ట్ 1 పార్ట్ 2 చదువుతాను లేదంటే ఓకే. అసిమెట్రిక్ నొటేషన్స్. Asymptotic notations are abstract notations for describing the behavior of algorithm and determining the rate of growth of a function. ఇప్పుడు ఫస్ట్ ఎక్స్పోనెన్షియల్ అనేది ఇంకా హైయెస్ట్, అది చాలా ఎక్కువ ఉంటుంది. దాని తర్వాత క్వాడ్రాటిక్ ఫార్మ్స్ 2n అలా ఉంటుంది. దాని తర్వాత లీనియర్, ఇది లైక్ లీనియర్ అంటే ఒక లైన్, ఒక మీడియం లాగా ఉంటుంది. సో ఇది సైజ్ పెరిగే కొద్దీ స్పేస్ రిక్వైర్మెంట్ కూడా పెరుగుద్ది. సో ఇది ఒక క్రాస్ లైన్ లాగా రెండింటితో పాటు పెరుగుద్ది, మిడ్ పాయింట్ లాగా. తర్వాత లాగిన్, ఇది ఎలా అంటే లైక్ ఎన్ లోపలే వచ్చేస్తుంది. సో ఇది తక్కువ. ఇంకా తర్వాత కాన్స్టెంట్, ఇది స్ట్రైట్ లైన్. సో ఎప్పుడు ఇది ఒక స్ట్రైట్ లైన్ లాగా వస్తుంది, నార్మల్గానే వెళ్తుంటుంది. ఇక్కడ లైన్ చూడు, కింద గ్రాఫ్లో అన్నీ స్టార్ట్ అయిన చోట స్టార్ట్ అవ్వలేదు కాన్స్టెంట్ది. ఒక 1 దగ్గర వచ్చి ఇంకా అలాగే పోద్ది కాన్స్టెంట్. ఓకే. బిగ్ O notation. Big O notation defines an upper bound of an algorithms. Therefore, it gives the worst case complexity of O of n algorithms. O of gn is equals to f of n. There exists a positive constants c and n naught such that big O of less than or equals to f of n less than or equals to c of gn for all n is greater than n naught. ఇప్పుడు ఇది వచ్చింది గ్రాఫ్. ఎఫ్ ఆఫ్ ఎన్ ఎన్ నాట్ వరకు తగ్గి తర్వాత పెరిగి మళ్ళీ తగ్గి మళ్ళీ పెరిగింది. ఎఫ్ ఆఫ్ ఎన్ ఈజ్ ఈక్వల్స్ టు ఓ ఆఫ్ జిఎన్. సిజీ వచ్చేసి సిజీ అంటే కాన్స్టెంట్స్. ఇది ఇలా పెరుగుతూ పెరుగుతూ పోతుంది, ఇలా ఉంటుంది గ్రాఫ్. తర్వాత ఒమేగా నొటేషన్. Omega notation represents the lower bound of the running time of an algorithm. Thus, it provides the best case complexity of an algorithm. లోవర్ బౌండ్ వచ్చేసి బెస్ట్ కేస్ లాగా అనుకోవచ్చు. ఇప్పుడు ఈ చూడు ఎన్ నాట్ ఉంది, సిజీ వచ్చేసి ఇలా ఒక ఫస్ట్ తగ్గి తర్వాత పెరుగుతూ పోయింది. అండ్ ఎఫ్ ఆఫ్ ఎన్ వచ్చేసి కాన్స్టెంట్ కాకుండా పెరుగుతూనే ఉంది, పెరిగి కొన్ని చోట్ల కాన్స్టెంట్గా ఉండి తర్వాత మళ్ళీ పెరిగింది, ఇలా వెళ్తూ ఉంటుంది. సిజీ ఈజ్ లెస్ దాన్ ఆర్ ఈక్వల్స్ టు ఎఫ్ ఆఫ్ ఎన్ అండ్ ఎఫ్ ఆఫ్ ఎన్ ఈజ్ గ్రేటర్ దాన్ ఎన్ నాట్. అది ఎన్ నాట్ పాయింట్ ఎక్కడ ఉందో చూడు. అండ్ సి ఈజ్ గ్రేటర్ దాన్ 0 అండ్ ఎన్ నాట్ ఈజ్ గ్రేటర్ దాన్ ఆర్ ఈక్వల్స్ టు 1. ఎఫ్ ఆఫ్ ఎన్ ఈజ్ ఈక్వల్స్ టు ఒమేగా ఆఫ్ జీ ఆఫ్ ఎన్. అండ్ theta notation. Theta notation encloses the function from above and below. It is used for analyzing the average case complexities of an algorithm. C1 g of n less than or equals to f of n less than or equals to c2 g of n. C1 into C2 is greater than or equal to 0, comma, n is greater than or equals to n naught and n naught is greater than or equals to 1. ఓకే. తీటాలో చూడు, ఫస్ట్ సి ఆఫ్ 1 జిఎన్, ఇది ఫస్ట్ ఇలా కొంచెం తగ్గుతూ కాన్స్టెంట్గా ఉంటూ పైకి వెళ్ళింది. తర్వాత ఎఫ్ ఆఫ్ ఎన్ వచ్చేసి ఇలా నార్మల్ పెరిగింది, బట్ ఒక చోట కాన్స్టెంట్గా ఒక చోట నార్మల్గా ఉన్నట్టు పెరిగింది. తర్వాత C2 ఆఫ్ జీ ఆఫ్ ఎన్ వచ్చేసి కాన్స్టెంట్గా పైకి పెరిగింది. ఇది ఎన్ నాట్ అనేది పాయింట్. ఎఫ్ ఆఫ్ ఎన్ C2 జీ ఆఫ్ ఎన్ కలిసే పాయింట్ ఎఫ్ నాట్ అనమాట. ఎఫ్ ఆఫ్ ఎన్ ఈజ్ ఈక్వల్స్ టు theta ఆఫ్ జీ ఆఫ్ ఎన్. Worst case analysis, the case that causes a maximum number of operations to be executed. Best case analysis, the case that causes a minimum number of operations to be executed. Average case analysis, we take all possible inputs and calculate the computing time for all the inputs, sum all calculates values and divide the function by the total number of inputs. Sorting, comparison based, counting based, two types ఉంటాయి. Comparison basingలో బబుల్ సార్ట్, సెలక్షన్ సార్ట్, ఇన్సర్షన్ సార్ట్, క్విక్ సార్ట్, మర్జ్ సార్ట్, హీప్ సార్ట్ వస్తాయి. కౌంటింగ్ బేసిస్లో బకెట్ ఆర్ రిడిక్ సార్ట్ వస్తాయి. ఈ బబుల్ సార్ట్స్ ఇవన్నీ చదివేదానికన్నా వాటి తాలూకా యానిమేషన్స్ చూస్తే క్లారిటీగా ఉంటాయి, కానీ ఇలా కూడా చదువుకుంటూ వెళ్దాం ఉంటుంది. ఓకే, bubble sort. Start with an array of unsorted numbers. Defines a function called bubble sort that takes in a array and the length of an array as a parameter. Arrayలో ఉన్న length of an array parametersగా తీసుకుంటుంది. In the function, create a variable called sorted that is in a set of false. Create for loop with the iterates through the array starting at index 0 and ending at the length of the array 1. And within for loop, compare the current element within the next element in the array. If current element is greater than the next element, swap their position and set sorted to true. After the for loop, check if the sorted is true. If sorted is true, or call the bubble sort function, and again with the same array and the length of the parameters. If the sorted is false, the array is now sorted and the function will return sorted. Call the bubble sort function and with the initialization unsorted array and its length as the parameters to be the sorting process. It is a stable sorting technique. A recursive iteration of bubble sort is t of n is equals to t of n minus 1 plus 1 plus n. It is in place sorting. Time complexity is equals to theta of n square. Space complexity is 1 plus n, theta of n. Worst case, best case వచ్చేసి O of n, worst case is O of n square, average square వచ్చేసి O of n square.
Algorithms in 60 seconds. Let's go. Today we're going to be covering bubble sort. Simple, easy to implement, but very slow. How does it work? Let's say we're given an array and we want to sort it in ascending order. We're going to compare adjacent pairs, and if they're out of order, we swap them. And now we're going to repeat this for the remaining adjacent elements in the array. The first pass,
ఇది
the
ఒకసారి
largest
జరిగింది
element
కదా.
is sorted. Second
ఇలా
pass, we repeat the same
ఎన్ని
process.
ఎలిమెంట్స్ ఉన్నాయో అన్నిసార్లు జరుగుతుంది.
In this case, it's already sorted, so we don't need to switch them. Last adjacent pair for the second pass. Second pass is done. Now we continue these passes until no more swaps are required. As you can see, the smaller elements bubble up towards the beginning, hence the name bubble sort. And finally, we have a sorted array. The runtime for bubble sort, worst case n squared, average case n squared, best case. Rhythms in 60 seconds. Let's go. Today we're going to be covering bubble sort. Simple, easy to implement, but very slow.
ఇది బబుల్ సార్ట్
How does
అన్నమాట. తర్వాత సెలెక్షన్ సార్ట్. బబుల్ సార్ట్ ఫస్ట్ లాస్ట్ది సెట్ అవుతుంది ఇలాంటివి చేసిన ఈ జరిగినప్పుడు. ఆ తర్వాత లాస్ట్ దానికి ముందర ఉండేవి సెట్ అవుతాయి. సో ప్రతిసారి చివరివి సెట్ అవుతాయి. సో ఫస్ట్ది లేటర్ ఇటరేషన్స్లో స్టార్టింగ్ పొజిషన్లో మార్పు జరుగుతుంది, కానీ లాస్ట్ పొజిషన్స్లో జరగదు. ఇది ఒక అబ్జర్వ్. బబుల్ సార్ట్ ఈజ్ ఈజీ టు అండర్స్టాండ్. and implement. It does not require any additional memory space. It is a stable storage algorithm, the meaning that elements hold the same key value and maintain their relative orders in the sorted updates. Disadvantages: bubble time complexity, worst case O of n square, average case O of n square, best case O of n. గుర్తుండిపోయింది ఎన్నిసార్లు అడగలేదు, టీసీఎస్లో కూడా అడిగాడు. తర్వాత సెలెక్షన్ సార్ట్.
Algorithms in 60 seconds. Let's go. Let's dive right into it. Today we're tackling selection sort. Selection sort is one of the simplest sorting algorithms and is really easy to implement. The only thing is, it's very slow. Let's go through a demonstration of how selection sort works using a list of numbers, where we want to sort the list in ascending order. The first step for selection sort is to go through the entire list and find the smallest number. After that, you want to swap the number to put it at the beginning. That number is now sorted. After that, we repeat the process with the rest of the unsorted numbers, finding the smallest number and swapping it with the beginning of the unsorted portion. We continue this process until we have a sorted list. Now, let's talk about the runtime complexity of selection sort. In the worst case, average case, and best case scenarios, selection sort has a slow time complexity of n squared because it runs basically the same regardless of the arrangement of the numbers. Algorithms in 60 seconds. Let's go. Let's dive right into it. Today we're tackling selection sort.
The core idea of selection sort is straightforward. Repeatedly find the smallest element in the unsorted portion of the array and move it to the end of the sorted portion. By continuously comparing and swapping, the array eventually becomes sorted. Let's see how it works with an example. Imagine we have an array 7, 4, 5, 9, 8, 3, 2. We'll use 3 pointers to help us. The pointer I marks the first element of the unsorted portion. The pointer min tracks the position of the smallest element starting at I. The pointer j scans through the remaining elements in the unsorted portion. In the first pass, both I and min start at the first element, 7. The pointer j begins scanning from the second element, 4. Whenever the element at j is smaller than the current minimum, we update min. After completing the scan, min points to the position of the smallest element, 2. We then swap the smallest element, 2, with the element at I, 7. The array becomes 2, 4, 5, 9, 8, 3, 7. In the second pass, I moves to the second element, 4, and min is reset to point at 4. The pointer j starts scanning from the third element. After the scan, min points to 3. We swap the smallest element, 3, with the element at I, 4. The array becomes 2, 3, 5, 9, 8, 4, 7. The subsequent passes repeat this process. Let's continue with the demonstration. By the end, the array is 2, 3, 4, 5, 7, 8, 9, fully sorted. Now, let's take a look at a Java implementation of selection sort. The selection sort function uses 2 nested for loops. The outer loop marks the beginning of the unsorted portion, while the inner loop identifies the smallest value in that portion. Once the smallest value is found, it is swapped with the first element in the unsorted portion, ensuring that the smallest value is placed in the correct position after each pass. Finally, let's analyze the complexity of selection sort. For an array with n elements, each pass scans the unsorted portion to find the smallest value, which takes on. Repeating this n times gives an overall time complexity of on squared. The space complexity is O1 since it's an in-place algorithm and doesn't need extra memory. The core idea...
Algorithms in 60 seconds. Let's go. Let's jump right into it. Today we're tackling a sorting algorithm called insertion sort. Insertion sort is a simple...
నెక్స్ట్ 60 సెకండ్స్ లో సెలెక్షన్ సార్ట్ నేర్చుకుందాం. బబుల్ సార్ట్ లో లాగా టూ అడ్జసెంట్ ఎలిమెంట్స్ ని కంపేర్ చేస్తూ స్మాలెస్ట్ ఎలిమెంట్ కనుక్కోకుండా సెలెక్షన్ సార్ట్ లో ఈచ్ పాస్ లో అరేలో ఉన్న అన్ని ఎలిమెంట్స్ ని ఒకేసారి కంపేర్ చేసి స్మాలెస్ట్ ఎలిమెంట్ కనుక్కొని దాన్ని తీసుకెళ్లి అరే స్టార్టింగ్ లో కరెక్ట్ పొజిషన్ లో పెడతాం టు సార్ట్ అరే ఇన్ అసెండింగ్ ఆర్డర్. ఇప్పుడు ఈ అరేని అసెండింగ్ ఆర్డర్ లో సార్ట్ చేద్దాం. ఫస్ట్ పాస్ లో అరేలో స్మాలెస్ట్ ఎలిమెంట్ ఫైండ్ చేస్తాం. ఈ అరేలో 0th ఇండెక్స్ నుంచి లాస్ట్ ఇండెక్స్ వరకు స్మాలెస్ట్ ఎలిమెంట్ ఏంటి? 11. సో అసెండింగ్ ఆర్డర్ లో స్మాలెస్ట్ ఎలిమెంట్ స్టార్టింగ్ ఉండాలి కాబట్టి 11 ని 0th పొజిషన్ లో ఉన్న 64 తో స్వాప్ చేస్తాం. ఫస్ట్ పాస్ అయ్యేసరికి అరే ఇలా ఉంది. 0th ఇండెక్స్ లో ఎలిమెంట్ ఫిక్స్.
అక్కడ స్వాప్ చేశారు అంటే ఈ నుంచి ఆడికి మార్చేశారు, రెండింటిని మార్చేశాడు, అది గుర్తుపెట్టుకో.
పోయింది బికాస్ అదే అరేలో స్మాలెస్ట్ ఎలిమెంట్ కాబట్టి. ఇంకా దీనికి అదిలేకుండా సెకండ్ పాస్ లో ఫస్ట్ ఇండెక్స్ నుంచి లాస్ట్ ఇండెక్స్ వరకు స్మాలెస్ట్ ఎలిమెంట్ ఫైండ్ చేస్తాం విచ్ ఇస్ 12. దీన్ని ఈ రేంజ్ లో స్టార్టింగ్ ఇండెక్స్ 1 లో ఉన్న 25 తో స్వాప్ చేస్తాం. సెకండ్ పాస్ అయ్యేసరికి అరే ఇలా ఉంది. 0 అండ్ ఫస్ట్ ఇండెక్స్ లో ఎలిమెంట్స్ ఫిక్స్ అయిపోయినాయి. ఇప్పుడు థర్డ్ పాస్ లో సెకండ్ ఇండెక్స్ నుంచి లాస్ట్ ఇండెక్స్ వరకు స్మాలెస్ట్ ఎలిమెంట్ ఫైండ్ చేస్తాం విచ్ ఇస్ 22. దీన్ని ఈ రేంజ్ లో స్టార్టింగ్ ఇండెక్స్ 2 లో ఉన్న 25 తో స్వాప్ చేస్తాం. థర్డ్ పాస్ అయ్యేసరికి అరే ఇలా ఉంది. ఫస్ట్ 3 ఎలిమెంట్స్ ఫిక్స్ అయిపోయి ఉన్నాయి. ఫోర్త్ పాస్ లో థర్డ్ ఇండెక్స్ నుంచి లాస్ట్ ఇండెక్స్ వరకు స్మాలెస్ట్ ఎలిమెంట్ ఫైండ్ చేస్తాం విచ్ ఈస్ 25. ఈ రేంజ్ లో స్టార్టింగ్ ఇండెక్స్ 3, 25 థర్డ్ ఇండెక్స్ లోనే ఉంది. సో ఎలాంటి స్వాప్స్ అవసరం లేదు బికాస్ దే ఆర్ ఆల్రెడీ ఇన్ కరెక్ట్ ఆర్డర్. ఫైనల్లీ వి గాట్ సార్టెడ్ అరే ఇన్ అసెండింగ్ ఆర్డర్. మన అరేలో ఎన్ని ఎలిమెంట్స్ ఉంటే n-1 పాసెస్ లో మన అరే సార్ట్ అయిపోతుంది. స్మాలెస్ట్ ఎలిమెంట్ ఫైండ్ చేయాలంటే అరేలో ప్రతి ఎలిమెంట్ ని రిమైనింగ్ ఎలిమెంట్స్ తో కంపేర్ చేయాలి కదా. For doing this, we need 2 nested for loops. అందుకే దీని టైం కాంప్లెక్సిటీ big of n square అవుతుంది. ఎక్స్ట్రా స్పేస్ ఏం యూజ్ చేయట్లే కాబట్టి స్పేస్ కాంప్లెక్సిటీ విల్ బి big of 1. ఇప్పుడు ఇన్స్టా క్లోజ్ చేసి సెలెక్షన్ సార్ట్ కోడ్ చేయండి. నెక్స్ట్ 60 సెకండ్స్ లో సెలెక్షన్ సార్ట్ నేర్చుకుందాం. బబుల్ సార్ట్ లో లాగా టూ అడ్జసెంట్ ఎలిమెంట్స్ ని కంపేర్ చేస్తూ స్మాల్
సెలక్షన్ సార్ట్ అనమాట. ఇప్పుడు దాని గురించి చదువుతాం. సెలక్షన్ సార్ట్ వచ్చేసి ద ఆల్గోరిథం ఇనిషియలైజ్ ద మినిమం వాల్యూ మ్యాక్స్ టెక్స్ to the location 0, traverse to array to find the minimum element in the array. While traversing, if any element smaller than min index found, the swap both values. Then increment min dax to the point to the next element. Repeat until the array is sorted. Recursive relation t of n is equals to t of n minus 1 plus n minus 1. Max swap is equals to n minus 1. Complexity is theta of n. Min swap is equals to 0. Iterative time complexity is O of n square. Either best అయినా worst అయినా ఏదైనా time complexity O of n square. Space complexity worst case కి best case కి average case కి O of n square. It is unstable sorting. ఓకే, తర్వాత insertion sort.
Algorithms in 60 seconds. Let's go. Let's jump right into it. Today we're tackling a sorting algorithm called insertion sort. Insertion sort is a simple algorithm that is slightly faster than selection sort, but is still very slow. Let's go through an example of sorting a list of numbers in ascending order using insertion sort. So, the algorithm starts by going to the first number. That number becomes the sorted portion. After that, you move on to the next number and compare it with entries in the sorted portion, inserting it where it should belong. We repeat this process with the rest of the list until it is sorted. Now, let's look at the time complexity of insertion sort. In the worst case and average case, the algorithm runs in n squared, but in the best case, when the list is already sorted, it runs in linear n time. Algorithms in 60 seconds. Let's go. Let's jump right into it. Today we're tackling
Okay, so this is an insertion sort. So we already know the first item is in order. So we don't need to look at that one. So we start with the king. King versus a 9. King is bigger than a 9, so it doesn't need to go before it. Then the 4. Is 4 less than a king? Yes. Is a 4 less than a 9? Yes. Done. 10. Is 10 less than king? Yes. Is 10 less than 9? No. Next. 2. Is 2 less than king? Yes. Is 2 less than 10? Yes. Is 2 less than 9? Yes. Is 2 less than 4? Yes. Done. Next item. 7. Is 7 less than king? Yes. Is 7 less than 10? Yes. Is 7 less than 9? Yes. Is 7 less than 4? No. Next item. Jack. Is Jack less than king? Yes. Is Jack less than 10? No. Done. And the final item is an ace. Ace is high, so is ace less than a king? No. So our items are all sorted. So 2, 4, 7, 9, 10, Jack, king, ace. Done.
ఇది ఇన్సర్షన్ సార్ట్ అనమాట, కార్డ్స్ లాగా. ఒకటి తీసుకొని అది ఎంత ముందరికి వెళ్తుంది అని దాని ముందర ఉన్న వాటిని కంపేర్ చేసుకుంటూ పోవాలి. Algorithms. To sort an array of size n in ascending order, iteration from array of 1 to array of n over the array. Compare the current element's key to its predecessor. If the key element is smaller than its predecessor, compare it to the elements before. Move the greater elements before. Move the greater elements of one position up to make space for the swapped element. Number of comparisons minus max is equals to n into n minus 1 by 2. Min is equals to n minus 1. Best case is equals to theta of n. Worst case and average case is equals to theta of n square. Insertion sort is equals to position plus shifting. If it's highly effective due to order of input. Recursive time is equals to t of n is equals to t of n minus 1 plus m. That is equals to theta of n square. Space is equals to theta of n. Stable sorting. తర్వాత quick sort. Quick sort వచ్చేసి డివైడ్ అండ్ కౌంటర్. ఇట్ ఈస్ అన్స్టేబుల్ సార్టింగ్. బెస్ట్ కేస్ ఇస్ ఈక్వల్స్ టు theta and theta n of log n and average worst case is equals to theta of n square. Recursive వచ్చేసి t of n is equals to 2t into n by 2 plus m. Using Master's theorem, theta of n log n, then నెంబర్ ఆఫ్ కంపారిజన్స్ వచ్చేసి n ఇంటూ n మైనస్ 1. క్విక్ సార్ట్లో కంపారిజన్స్ చెప్పొచ్చు n ఇంటూ n మైనస్ 1 బై 2. ఇన్సర్షన్ సార్ట్లో నెంబర్ ఆఫ్ కంపారిజన్స్ వచ్చేసి n ఇంటూ n మైనస్ 1 బై 2. క్విక్ సార్ట్కి ఇన్సర్షన్ సార్ట్కి సేమ్. మిగతా చోట కంపారిజన్స్ గురించి అడగలేదు. క్విక్ సార్ట్కి ఇన్సర్షన్ సార్ట్కి కంపారిజన్స్ వచ్చేసి n ఇంటూ n మైనస్ 1 బై 2. That's what happened.
Algorithms in 60 seconds. Let's go. Today we're looking at quicksort, which is an efficient, reliable, and popular algorithm that uses recursion. We'll go through a simple example step by step. First, we pick a pivot, which is any element in the array. It could be the first, middle, last, or any random element. For the sake of this example, we'll use the last. The algorithm is simple from there. The numbers that are less than our pivot will go to the left of it, and the numbers that are larger go right. So 9 will go right, 2 will go left, and so on. We then recursively sort the left and right sections. Since our right side only had one number, it's already sorted. So we'll look at the left, where 1 is the pivot. Looking through the numbers, we again put them to the left or right of our pivot. Continue doing this process until every left and right section can be considered sorted. algorithms in 60 seconds.
Today, we're going to learn about quicksort, a fast and efficient sorting algorithm based on the divide and conquer principle. Quicksort works in 3 steps. First, choose a pivot. The pivot is an element that helps divide the array. You can pick it randomly or use the first or last element. A good pivot reduces recursion depth, making sorting faster. Second, partition the array by splitting it into 2 parts. The left part contains elements smaller than the pivot, and the right part contains elements larger than the pivot. The pivot ends up in its final sorted position. Third, recursively sort the 2 parts. Repeat this process for each part until every subarray has just 1 or no elements, and the array is fully sorted. Let's look at an example with the array 22, 7, 12, 15, 1, 6, 8. We'll pick the last element, 8, as the pivot. We use the Lamuto partition algorithm. First, initialize 2 pointers. Pointer I starts at -1, tracking elements smaller than the pivot, and pointer J starts at the first element and compares each to the pivot. Now, process each element. First, 20 is greater than 8, so do nothing. 2 is smaller than 8, so increment I to 0 and swap 2 with 20. Next, 7 is smaller than 8, so increment I to 1 and swap 7 with 20. 12 and 15 are greater than 8, so skip them. 1 is smaller than 8, increment I to 2 and swap 1 with 20. Finally, 6 is smaller than 8, increment I to 3 and swap 6 with 12. After processing all elements, I is at position 3. Now swap the pivot, 8, with the element at I plus 1, which is 15. The array becomes 2, 7, 1, 6, 8, 20, 12, 15. The pivot, 8, is now in its final position, splitting the array into 2 parts. The left part contains elements smaller than 8, and the right part contains elements larger than 8. Repeat the same steps for both parts until the entire array is fully sorted. Quicksort is efficient because it splits the array into 2 parts with each partition, making recursion depth proportional to log n. At each recursion level, operations take O(n) time. Therefore, the average time complexity is O(n) log n. However, in the worst case, such as when the array is already sorted, quicksort's time complexity can degrade to O of n squared. Here's the pseudocode for quicksort. The quicksort function calls the partition function to find the pivot's position, splitting the array into 2 parts. Then, quicksort is recursively applied to each part. Today, we're going
అనేది పివట్. నెక్స్ట్ 4 కన్నా 5 అనేది పెద్దగా ఉంది, అండ్ 4 కన్నా 3 అనేది తక్కువ ఉంది, తక్కువ లేదా ఈక్వల్గా ఉంది. సో ఈ రెండింటిని ఎక్స్చేంజ్ చేయాలి. ఒక పార్ట్ 4 కన్నా తక్కువ లేదా ఈక్వల్గా ఉంది, సో దాని ముందర ఉండేదాన్ని దీన్ని రెండింటిని ఎక్స్చేంజ్ చేయాలి. నెక్స్ట్ 6ని 4ని ఎక్స్చేంజ్ చేయాలి. సెట్ అయింది. పివోట్ కన్నా 6 అనేది ఎక్కువ ఉంది, ఐజే దాని నుంచే స్టార్ట్ అయినాయి. తర్వాత జే ఇంక్రిమెంట్ అయింది, తర్వాత ఐ ఇంక్రిమెంట్ అయింది. దానికన్నా ఎక్కువ దీనికన్నా తక్కువ ఉన్నాయి కాబట్టి ఆ రెండింటిని ఎక్స్చేంజ్ చేసినాం. తర్వాత ఇంకొకటి చూసాము, ఐ పొజిషన్ ఉంటుంది, జే పొజిషన్ కదిలింది. తర్వాత ఐ పొజిషన్ జే పొజిషన్ ఉండేది ఎక్స్చేంజ్ అయ్యేది. తర్వాత జే పొజిషన్లో ఉండేది పివోట్ కన్నా తక్కువ ఉంది, సో దాని నెక్స్ట్ ఐ పొజిషన్ తర్వాత ఇప్పుడు చూపిస్తున్న జే పొజిషన్ మారింది. దాని తర్వాత 4, 6 పొజిషన్స్ నుంచి మారిపోయాయి. క్విక్సార్ట్ ఇంకా కాస్త డిఫరెంట్గానే వచ్చింది. సో మళ్ళీ చూడాలి. సార్ట్ ఓకే, డివైడ్ చేసుకుంటూ వెళ్ళి సార్ట్ చేసి కలిపి కలుపుకుంటూ రావాలి. Merge sort is array of 1 L, R if R is greater than 1. Find the midpoint to divide the array into two halves. Middle m is equals to 1 plus or minus 1 by 2. Call merge sort of the first half. Call merge sort array of 1 comma m. Call merge sort of the second half. Call merge sort array of m plus 1 comma r. Merge with the two halves sorted in step 2 and 3. Call merge sort array of 1 comma m comma r. It is table sorting. It is pure divide and conquer. Recursive t of n is equals to 2t into n by 2 plus n. Complexity best case is equals to average case is equals to worst case is equals to t2 of n log.
Algorithms in 60 seconds. Let's go. Today we're tackling a sorting algorithm called merge sort. Merge sort is an algorithm that uses a divide and conquer logic to reduce runtimes. Let's see an example. The algorithm starts by dividing the array into two smaller arrays. You keep dividing the arrays until the smallest subarray is just a single unit. If there are any that still have two elements, break them up and make sure that they're sorted. This will happen if the array is of an odd length. From there, you can start merging. This is done by going through pairs of the subarrays, comparing the leftmost and therefore smallest entries until all elements are in a new sorted array. We repeat this process until everything is sorted. Now, let's take a look at the time complexity of merge sort. In the worst case, average case, and best case, it will take n log n, since merge sort always divides the array into two halves and takes linear time to merge them. Algorithms in 60 seconds. Let's go. Today we're tackling
This is how to do a merge sort. Now recursively, we're going to get the middle index and split the array in two, so the left will be 3 and 4, and the right will be 5 and 2. Then we do this again. The left splits to 3 and 4, and the right side will split to 5 and just 2. At this level, we hit our base case, and notice all of these arrays are sorted because they just have one element. Now the act of splitting the arrays in two is what we call the divide step. Now we need to do what is called the conquer step, and this is to merge each of the arrays together. So to sort 3 and 4, well, that's pretty easy. That's already sorted. But to sort 5 and 2, we would need to flip their order. Now we need to do this again, and more precisely, we'd have an index I and an index j. So the first element we'd want to use is the 2, and then we move over j. Then we'd want to use the 3, and so we can move over I. We then use the 4 and move over I, and we finally use the 5, and now we have a sorted array. Subscribe to the channel for more. This
Hi everyone, welcome back to the Big O series. Today we're talking about a time complexity that's a bit more complicated than O of n, but nowhere near as bad as exponential. It's called O of n log n, sometimes referred to as quasi-linear time. You'll see it a lot in efficient sorting algorithms. In this video, we'll use merge sort as a concrete example to understand what O of n log n really means. Before we jump into merge sort, let's first look at a simple operation, merging two sorted arrays. For example, take the arrays 1, 3, 5, and 2, 4, 6, 7, 8. We can use two pointers, one pointing to the first array and the other pointing to the second. Each time, we compare the numbers the pointers are looking at. We take the smaller one, put it into the result array, and move that pointer forward. We repeat this step until one array runs out, and then we simply attach the rest of the other array. In this whole process, each element is visited at most once. So the time complexity of merging two sorted arrays of length m and n is O of m plus n. If the arrays are about the same size, that's O of n. Now that we've got the basics, let's look at merge sort. The idea of merge sort is to break a big array down into many tiny arrays with just one element each. Then, we keep merging them back together, two at a time, using the same method we just talked about until everything is sorted. Here's how we can think about it using a queue. Imagine we want to sort an array with 8 elements. At the start, we put each element into the queue as a separate one-element sorted array. Then, each time, we take two arrays from the front of the queue, merge them into a larger sorted array, and put the result back into the queue. After the first round of merging, we have 4 arrays, each containing 2 sorted elements. After the second round, we have 2 arrays, each containing 4 sorted elements. After the third round, there's only 1 array left, with all 8 elements sorted. That's our final result. So why does merge sort run in O of n log n? The reason is that each round of merging scans the entire array once, which costs O of n, and the number of rounds is about log n. For example, 8 elements need 3 rounds, 16 elements need 4 rounds, and so on. Multiply those together, and you get O of n log n. Finally, here's the Python code for what we just discussed. It has 2 functions. The first one is merge, which merges 2 sorted arrays. The second one is merge sort, which uses a queue to implement merge sort. Hi everyone, welcome back to the Big O series.
What is merge sort we are going to see with an example. So here we are going to have an array which is unsorted. Here we are having formula mid is equal to left plus right divided by 2, and we are going to use it and you will get the mid. After getting mid, you are going to divide the array in 2 parts. Again, the 2 arrays are going to be divided in 2 parts. So we are going to divide it until and unless we are not going to get the single elements. So here we are going to create a new array of 2 size. We'll compare 12 with 11. So first 11 we are going to place, then 12. Then there is 13 at the index number 2. We are going to have again the array of size 3. We are going to compare 11 with 13. 11 smaller we are going to place it. We are going to compare 12 with 13. 12 is smaller we are going to place it, and 13 we are going to place it. Similar with the right side. So here the condition comes I should be less than equal to j. So here I is 11 and j is 5. So 5 is smaller we are going to place it, and we are going to update the j. Compare 11 with 6. 6 is smaller we are going to place it. Now here 7 is also smaller we are going to place it. So the remaining array present at the left side, it is already sorted. So we are going to place it as it is inside the array. Time complexity big O of n log n. What is merge sort?
ఓకే, ఇది మర్జ్ సార్ట్ అనమాట. మర్జ్ సార్ట్ ఈజ్ array of L that's on T of n. Call the merge sort in the first half. Call merge sort array of L. One array of merge sort array comma 1 comma n. Call the merge sort for the second half. The array merge sort array of m plus 1, అదే m plus 1 comma r. అక్కడ అనేది L అనుకుంటా. Merge the 2 halves are sorted. In the step 2 and 3, call merge the array of 1 comma n comma r. If the stable sorting, it is a stable sorting. It's a q divide and conquer recursive. T of n is equals to 2t into n by 2 plus n. Complexity best average worst case complexity is O of n log n. తర్వాత radic sort. It is a count based sorting. It is a outplus sorting. Q of n comma k. If n is greater than k, that is equals to q of n, and if n is k equals to k, that is equals to q of n square. With the time complexity is q into r of n into r space complexity. radic sort మీద కూడా కొన్ని క్వశ్చన్స్ చూసాను నేను. ఒక్కటి ఇస్రోలో చూసాను. సో అప్పుడు దీని గురించి తెలుసుకొని పెట్టుకున్నాను. ఇది చాలా ఈజీ.
The radic sort algorithm starts by sorting all the numbers based on their least significant digit. While arranging the numbers, the relative positioning remains the same. After the first pass, it arranges the numbers again, based on the next, more significant digit. When a digit is shorter than others, it is assumed that it proceeds with zeros. Now the process repeats until the most significant digit is reached. Now, arranging the numbers in each iteration takes linear time complexity, and the number of times it arranges is the same as the number of digits in the largest number, so the overall time complexity would be big O of k times n. Now, to understand a more detailed analysis of the algorithms, subscribe and check the longer videos on the channel.
radic sort అనేది పెద్ద కష్టం కాదు, కానీ ఎక్కువ వాడలేదు కాబట్టి గుర్తుకుండకపోవచ్చు. ఫస్ట్ అన్ని నెంబర్స్లో ఉన్న లాస్ట్ డిజిట్ని బట్టి వాటిని సార్ట్ చేసుకోవాలి. అదే లాస్ట్ వచ్చేసి 3 డిజిట్స్ అన్నీ 3 డిజిట్స్ చేయాలి. 3 డిజిట్స్ చేయాలంటే 2 డిజిట్ నెంబర్స్కి ముందర జీరోస్ యాడ్ చేయాలి. అండ్ లాస్ట్ దాన్ని యూనిట్ ప్లేస్లో ఉండేదాన్ని స్టార్టింగ్ యూనిట్ ప్లేస్లో ఉండేదాన్ని బట్టి సార్టింగ్ చేయాలి. తర్వాత దాని నెక్స్ట్ ప్లేస్లో ఉండేదాన్ని బట్టి సార్టింగ్ చేయాలి. దాని తర్వాత దాని ముందర ఉండే ప్లేస్ దాన్ని బట్టి సార్టింగ్ చేయాలి. సో ఇలా మొత్తం అదే స్టార్ట్ అయిపోతుంది. సార్ట్ ఈజీయే, కాకపోతే తక్కువ సార్లు వాడాం కాబట్టి గుర్తున్నది. ఇంక ఇప్పటి నుంచి రికర్షన్ వస్తుంది. స్టోరీలోకి రికర్షన్ వచ్చాడయ్యా, వచ్చిందండి వయ్యారి. రికర్షన్. A recursion is an equation or inequality that describes a function in terms of its values or on smaller inputs. To solve a recursion relation means to obtain a function defined on the natural numbers that satisfy the recurrence. There are 4 methods for solving recursions: substitution method, iteration method, recursion tree, master method. Substitution method: t of n is equals to 1 to n is equals to 0, t of n minus 1 plus 1, n is greater than 0. ఇప్పుడు t of n వచ్చేసి t of n minus 1 plus 1. t of n అంటే t of n minus 1 plus 1 అనమాట. t of n minus 1 అంటే t of n minus 2 plus 1 అనమాట. ఇది ఇట్లా ఈక్వేషన్ పోతుంది. t of n minus 1 సిచ్యుయేషన్ అంటే ఏంటి? t of n minus 2 plus 1 whole plus 1 ఫ్రమ్ ఈక్వేషన్ 2. సో ఇలా చేసుకుంటూ పోతే కౌంట్ ఆఫ్ 4 టైమ్స్. ఇది t of n is equals to t of n minus k plus k. Assume n minus k is equals to 0, n is equals to k అనుకుంటే k వాల్యూ n వాల్యూ సేమ్ అనమాట. సో k వాల్యూ n అని వేసుకుంటే t of n is equals to t of n minus n plus n. t of n is equals to t of 0 plus n. t of 0 అంటే 1 అనమాట. సో t of n is equals to 1 plus n, that is equals to theta of n. ఇది సబ్స్టిట్యూషనల్ మెథడ్. ఇది రికర్షన్ మెథడ్కి వస్తే t of n is equals to 1 if n is equals to 0, t of n minus 1 plus n if n is greater than 0. t of n ఉందా, అది n వస్తాయి. ఆ n నుంచి n లేదా t of n minus 1 యూస్ చేస్తే n minus 1 వస్తాయి, లేదా t of n minus 1 లేదా t of n minus 2 యూస్ టు n minus 2 వస్తాయి. t of n minus 2 లేదా t of n minus 3 gives to n minus 3. ఇట్స్ ఆన్ t of 2 నుంచి 2 వస్తుంది, లేదా t of 1 is equals to 1 వస్తుంది, లేదా 1 వస్తుంది. t of 0 అంటే 0. సో ఈ వాల్యూస్ అన్నిటిని, ఈ కింద నుంచి వచ్చిన వాల్యూస్ అన్నిటిని యాడ్ చేస్తే 0, 1, 2 అండ్ సో ఆన్ n minus 3, n minus 2, n minus 1, n. ఇవన్నీ యాడ్ చేస్తే సమ్ ఆఫ్ n న్యాచురల్ నెంబర్స్ లెక్క n ఇంటూ n ప్లస్ 1 బై 2. t of n is equals to t of n into n plus 1 by 2, theta of n square. ఇప్పుడు ఇటరేషన్ మెథడ్ అన్నమాట. t of n is equals to 1 to 1, n అనేది ఇప్పుడు వస్తుంది అంటే n is equals to 0, t of n minus 1 plus n is greater than 0. t of n is equals to t of n minus 1 plus n. t of n is equals to t of n minus 1 plus 2. t of n is equals to t of n minus 1 plus n minus 1 plus n. ఇది ఫస్ట్ది. t of n minus 1 వచ్చేసి t of n minus 2 plus n minus 1కి ఈక్వల్. సో ఇలా t of n వాల్యూస్ వచ్చేసి t of n minus 2 plus n minus 1 plus nకి ఈక్వల్ కాబట్టి దీని ఒక సెకండ్ ఈక్వేషన్ లెక్క తీసుకో. తర్వాత థర్డ్ ఈక్వేషన్ ఏంటంటే t of n minus 3 plus t of n minus 2 plus n minus 1 అనమాట, ప్లస్ n. ఇది 3. కంటిన్యూ ఫర్ k టైమ్స్ ఇలానే చేస్తే t of n ఏమొస్తుంది అంటే t of n minus k ప్లస్ t of n minus into k minus 1 plus t of n minus k minus 2 and so on n minus 1 plus 1 n వస్తుంది. అజ్యూమ్ n minus k is equals to 0, n equals to k అనుకుంటే ప్లేస్లో t is equals to 0, 1, 2, 3 and so on n minus 1 plus n వస్తుంది. సో ఈ ఈక్వేషన్ ప్రకారం 1 plus n into n plus 1 by 2. ఓకే, t of n is equals to 1 plus n into n plus 1 by 2 is equals to theta of n square. t of n is equals to 2t n minus 1 plus 1. By solving the recursion tree, 1 plus 2 plus 2 cube plus and so on 2 power k is equals to 2 power k plus 1, that is equals to theta of 2 power n. దిస్ ఈజ్ ఇన్ జీపీ సిరీస్లో ఉంది కాబట్టి అలా వాడతాం. తర్వాత మాస్టర్ థియరం ఫర్ డిక్రీజింగ్ ఫంక్షన్. T of n is equals to a of t and into n minus b plus f of n. A is greater than 0, b is greater than 0, and f of n is equals to O of n power k, where k is greater than or equals to 0. Case: if a is less than 1, O of n power k, O of f power of n. If a is equals to 1, O of n power k plus 1 and O of n into f power of n. If a is greater than n, O of n power k into a power n by b, O of f into a n into a power n by b. Master theorem for dividing function. Log b a, t of n is equals to a into t into n by b plus f of n. A is greater than or equals to 1. Case 2, b is greater than f of n is equals to theta of n power k log of b log power p into n. Case: if log b power a greater than k, then theta of n log b power a. Case 2, if log b power a equals to k, base b log a power k. If p is greater than minus 1, t is equals to n power k log of p plus 1 into n. If p is equals to minus 1, theta is equals to n power k log into log of log n. If p is less than 1, theta of log theta n power k. Case 3, if log b power b to the power a less than k, if p is greater than or equal to 0, theta is equals to n power k log p n. If p is less than 0 of 0, O of n power k అవుతుంది అనమాట. T of n is equals to 2 power t of n by 2 plus 1 వస్తుంది. A is equals to 2, b is equals to 2. If f of n is equals to 0, O of 1 అవుతుంది. Theta is equals to n power 0 log power 0 and n. log 2 base 2 వచ్చేసి equals to 1 అవుతుంది. So greater than k is equals to 0. Case theta is equals to theta of n minus n power 1 రికర్సివ్ రిలేషన్లో, దీని ప్రకారం రికర్సివ్ రిలేషన్లో టీ ఆఫ్ ఎన్ వచ్చేసి టీ ఇంటూ ఎన్ మైనస్ 1 ప్లస్ 1 అయినప్పుడు ఓ ఆఫ్ ఎన్ అవుద్ది, బిగ్ ఓ ఆఫ్ ఎన్. టీ ఆఫ్ ఎన్ ఇస్ ఈక్వల్స్ టు టీ ఆఫ్ ఎన్ మైనస్ 1 ప్లస్ 1 అయినప్పుడు ఓ ఆఫ్ ఎన్ స్క్వేర్ కూడా అవుద్ది. టీ ఆఫ్ ఎన్ ఇస్ ఈక్వల్స్ టు టీ ఆఫ్ ఎన్ మైనస్ 1 ప్లస్ లాగ్ ఎన్, ఓ ఆఫ్ ఎన్ లాగ్ ఎన్ కూడా అవుద్ది. టీ ఆఫ్ ఎన్ ఇస్ ఈక్వల్స్ టు టీ ఆఫ్ ఎన్ మైనస్ 1 ప్లస్ 1 ప్లస్ ఎన్ స్క్వేర్ ఇస్ ఈక్వల్స్ టు ఓ ఆఫ్ ఎన్ క్యూబ్ అవుద్ది. T of n is equal to T of n minus 2 plus 1 n by 2 O of n అవుద్ది. T of n is equal to T of n minus 100 plus n is O of n square అవుద్ది. ఇక్కడ ఈ రెండిటికి ఒకటే వాల్యూ వచ్చింది. కామన్ రికరెన్స్ రిలేషన్స్ యూజ్డ్ టు describe T of n is equals to T of n minus 1 plus 1. T of n is equals to T of n minus 2 plus 1, so on. లీనియర్గా వచ్చినప్పుడు ఓ ఆఫ్ ఎన్, క్వాడ్రాటిక్ వచ్చినప్పుడు ఓ ఆఫ్ ఎన్ స్క్వేర్ అవుతాయి. ఇక్కడ ఎక్స్పాన్షన్ ఎట్లా అంటే 1 ప్లస్ 1 ప్లస్ 1 అన్నట్టు తయారైంది. ఇక్కడ ఎక్స్పాన్షన్ ఏంటంటే n ప్లస్ n మైనస్ 1 ప్లస్ n మైనస్ 2 ప్లస్ అండ్ సో ఆన్ అట్లా తయారైంది. సో ఇక్కడ సింప్లిఫికేషన్ ఓ ఆఫ్ ఎన్ స్క్వేర్ అవుతుంది, n ఇంటూ n ప్లస్ 1 బై 2. తర్వాత హఫ్మ్యాన్ కోడింగ్. Huffman coding is a famous greedy algorithm. It is used for lossless comparisons of data. It is used variable length in encoding. It assigns variable length code to all the characters. Prefix rules. Huffman coding implements a rule known as a prefix coding. This is to prevent the ambiguities while decoding. It ensures that the code assigned to any character is not a prefix of the code assigned to any other character. There are two major steps in Huffman coding. Building a Huffman tree from the input characteristics, assign code to the characters by traversing the human tree. Huffman tree ఏంటి అంటే, step 1, create a leaf node for each character of the test. Leaf node of the character contains the occurring frequency of the character. అదే occurring frequency వస్తుంది అన్నమాట. Step 2, arrange all the notes in increasing order to their order of their frequency value. Considering the first two notes having minimum frequency. The frequency of this new code is the sum of the frequency of those two codes. Step 3, make the first node as the left child and the other node as the right child of the newly created node. Step 4, keep repeating step 2 and step 3 until all nodes from a single tree. Time complexity. Extract min is called 2 into n minus 1 times of there are n nodes as exact min cells heapify if take O of n O of log time. Thus overall time complexity of Huffman coding becomes O of n log n. Example ABC ABB CD BCC DAABB EEE BEAB ఉంది. ఇక్కడ హాఫ్మ్యాన్ ట్రీలో ఏంటండి 20 నుంచి 8. ఇప్పుడు చార్ట్ ఫ్రీక్వెన్సీ ఏ వచ్చేసి 4 టైమ్స్ వచ్చింది ఫ్రీక్వెన్సీ కోడ్. 0 1 బి వచ్చేసి 7 ఉంది, 1 1 ఉంది. ఫస్ట్ దానికి ఆన్సర్ 2 అయితే 1 అయితే, సెకండ్ దానికి ఆన్సర్ 3 అయితే అది 7 అయింది. సి వచ్చేసి 3 వచ్చింది, డి వచ్చేసి 3 వచ్చింది, 101 101. ఈ వచ్చేసి 4 వచ్చేసింది, 0 0. ఓకే, ఇక్కడ ఏబిసిడి వాల్యూస్ ఇలా ఉన్నాయి. 4 ఏ వాల్యూ 4 దగ్గర ఉంది, బి వాల్యూ 7 బి దగ్గర ఉంది, డి వాల్యూ ఉంది, సి వాల్యూ ఉంది.
Everybody, I am going to construct the Huffman algorithm for the following. Here A, B, C, D, E, letters are there and the frequencies of the letter are these 50, 10, 30, 5, 3, 2. We need to construct Huffman tree using Huffman algorithm. First of all, we need to select two minimum number. Here 2 and 3 are added together. That is 8, 2 and E3 added together. We will get 5. That is equal to 50, 10, 30, 5 and 5. Next to minimum are number 5 and 5. 5 is for D. That is D5 and 5 and 5 are added. We will get 10. That is 8, 2 and E3. Now the new minimum numbers are 10, 50, 10, 30 and 10. Then the next to minimum number 10 and 10. And 10 are added. This 10 for B. In B 10 and 10 and 10, that is equal to 20. Remaining 3s that is equal to D5 5 8 2 and E3. Now 50 30 20. Next remaining numbers. Now we need to add 20 and 30. 20 and 30 are added. That is equal to 20 10 10 D5 5 8 2. These are external node in the rectangle shape, and circle they are known as internal node. 20 and 30 are added. 30 for C30, and we will get 50. Now the last node is 50 and 50 are there. 50 for A, So construct the tree, that is 100, and this one is A 50. So in the last step I have done two numbers, that is for 50 30 20 and 50 and 50. So this is known as Hopman tree, and the Hopman codings are there 0 1 0 1 0 1 0 1 0 1. Now A for 0, B for 1 0 0, C for 1 1, D for 1 0 1 0, E for 1 0 1 0, E for 1 0 1 1 1, E for 1 0 1 1 1, A for 1 0 1 1 0, 1 0 1 1 0. Be ready. I am going to be ready. I am going to construct the Hopman algorithm for the following. Here A, B, C, D, E, letters are there, and the frequencies of the letter are these 50, 10, 30, 5, 3, 2. We need to construct Hopman minimum frequency among all the frequencies. Here
ये ऑफिस का काम करते करते थक चुका हूँ.
minimum frequency among all the frequencies. Here 5 and 9, then we need to add 5 and 9. So this is the step 1, A 5 and B 9 are added. We will get 14. 14 is the internal node. These are node and external node AB. Now in step 2, next minimum cost here, if we add 14 plus 12, then we will get 26. But if we add 12 plus 13, then we will get 25. So we will select the 25, that is C 12 and D 13 are selected, and we will get the cost is 25. And here 14 will remain same as previous. Now in step 3, now next to minimum cost is that is we need to select 14 and 16, then we will get 14 and 16 30. So 25 is there, C 12, D 13, we need to select E, that is 14, and next one is 14 plus 16, that is equal to 30. E 16, A 5, B 9. Now in step 4, we will add two minimum here. 25 and 35 are added together, we will get 55. 55 25, C 12, D 13, and here that is 30, 14, A 5 and B 9, C 16. Now last node is F, that is 45, that is A 45 and 55 added together, we will get 100. This is step 4 and step 5. Now we need to find the coding. We know the left branch is 0 and right is 1 0 1 0 1 0 1 0 1 and end. Now for A, first of all A coding is 1 1 0 0 1 1 0 0. For B 1 1 0 1 1 1 0 1. For C 1 1 1. For D 1 0 1 1 0 1. For E that is equal to for E this is E 111 E is 111 E is 111 C is 100 100 and F is 0. Minimum frequency among all the frequencies here 5 and 9, then we need to add
How to generate Huffman code for this given?
यहाँ पर हमें क्वेश्चन दिया गया है जहाँ पर
How to generate Huffman code for this given data? Already we have constructed Huffman tree with this character and probability. I will provide the link in the description for your reference. Now we have to generate Huffman code for each corresponding character or alphabet. How to generate Huffman code in the sense? You need to consider the Huffman tree. In this Huffman tree, what are the left subtree nodes present? You have to mark the code as 0, and for right subtree nodes, mark the code as 1. Left subtree 0, right subtree 1, 0, 1. Next, what is the code for A in the sense? Consider where the alphabet exactly presents. Here it presents in the leaf node. From the root node to the path towards its leaf node where the particular alphabet presents, you need to consider the code. Code for A is 0, 1. Code for B is 1, 1, 1. Triple 1 is the code for B. For C it is 1, 0. For D it is 1, 1, 0, 0. For E it is 0, 0. And for hyphen it is 1, 1, 0, 1. So this is the Huffman code for its corresponding alphabets. How to generate Huffman code for this given data? Already we have constructed Huffman tree with this character and probability. I will provide the link in the description for your reference. Now we have to generate Huffman code for each corresponding character or alphabet. How to generate Huffman code in the sense? You need to consider the Huffman tree. In this Huffman tree, what are the left subtree nodes present? You have to mark the code as 0, and for right subtree nodes, mark the code as 1. Left subtree 0, right subtree 1, 0, 1. Next, what is the code for A in the sense? Consider where the alphabet exactly presents. Here it presents in the leaf node. From the root node to the path towards its leaf node where the particular alphabet presents, you need to consider the code. Code for A is 0, 1. Code for B is 1, 1, 1. Triple 1 is the code for B. For C it is 1, 0. For D it is 1, 1, 0, 0. For E it is 0, 0. And for hyphen it is 1, 1, 0, 1. So this is the Huffman code for its corresponding alphabets. How to generate Huffman code for this given data? Here it presents in the leaf node. From the root node to the path towards its leaf node where the particular alphabet present, you need to consider the code. Code for A is 0, 1. Code for B is 1, 1, 1. Triple 1 is the code for B. For C it is 1, 0. For D it is 1, 1, 0, 0. For E it is 0, 0. And for hyphen it is 1, 1, 0, 1. So this is the
Hi, the topic is Huffman coding. Huffman coding is a compression technique. It is used for reducing the size of data or message. Suppose you want to store the data in a file, so you can store the data in compressed form to reduce the size of a file. When the data is sent over a network, data can be compressed and sent to reduce the cost of transmission. In this video, I am going to explain you if a normal message is sent, what will be the cost, and what is the fixed size encoding, then what is variable size encoding, that is Huffman coding. Now let us study the problem. I have a message here. Now this message I want to store it in a file or I want to send it over a network. Then let us understand what will be the cost of a message. So the cost of this message or the size of the message will be measured in terms of bits. Let us check. First of all, there are 20 letters in this one. So the length of this message is 20.
यूपीआई पेमेंट फेल हो गया, इसलिए दोस्त से फेवर मांगना पड़ा.
Next, how this message has to be sent? It has to be sent by using ASCII code. Electronic devices or computers all use ASCII codes for characters or English alphabet. So these are all characters. ASCII codes are 8 bits. I have used alphabets A to E here, so that is easy to understand for us. So if I say A, its ASCII code is 65, and the binary form is this one. So total 8 bits, these are 8 bits that are representing decimal 65, and that is representing A. Similarly, if I say B, then it is 66. This will be for 66. Likewise, C, D, E. For everyone we have, there is a 67 and 68 and 69, and here the binary code will be there. So 8 bits are there for each alphabet. Now if normally this message is sent 8 bits for each alphabet, then total number of bits will be how much? As there are 20 alphabets in this message, so this will be 8 into 20, that is 160 bits. size of the message will be 160 bits. Now this is a simple message to send without encoding. The size will be 160 bits, 8 bit for each alphabet. Now let us look at, can we use our own codes instead of ASCII codes? How it is possible? See, I'm not using all English alphabets or all possible symbols on the keyboard. I'm not using every symbol from the character set. I'm using only 5 alphabets, that 2 capital letters. Then, do I need 8 codes, 8-bit codes for representing just 5 alphabets? No. Few bits are sufficient. So can I use my own codes with less amount of bits? Yes. So next we will see fixed size codes. Here I have taken alphabets in this message, and how many times each alphabet is appearing, I have written the count here, or you can also call it as frequency. A is appearing 3 times, 1, 2, 3. Likewise, you can check all, how many times they are appearing, I have written them here. Total there are 20 alphabets. If you want to see the frequency, then you can say this is 3 by 20, that's 3 by 20, or this is 5 by 20, because total number are 20, so this is 6 by 20, and you can take the ratios. I prefer taking counts, that is easy for working. Even what should be the code? See, I have 5 characters. I don't need 8 bits for just 5 characters. 8-bit ASCII codes are for 128 characters or 128 symbols, but for only 5, let us see. If I have just 1 bit, then either I can write 0 or 1. So how many symbols I can represent? How many characters? Only 2 characters. If I have 2 bits, then how many I can represent? I can write 0, 0, 0, 1, 1, 0, 1, 1. So I can have 4 different combinations, and each combination can represent 1 symbol. But I have 5, so for that I can take 3 bits. So in this, how many combinations are possible? 0 to 7, that is 8 combinations are possible. So I will take 5 out of that. So let us say in 3 bits I will say A is 0, 0, 0, B is 0, 0, 1, C is 0, 1, 0, D is 0, 1, 1, and E is 1, 0, 0. I have given my own 3-bit codes. I will use this for encoding this message. And I will this will reduce the size of the message. So it means here instead of writing ASCII code, I will be writing 001 for B and 010 for C. Likewise, go on. When the message is encoded using this one, then what will be the size of the message? As we know well that there are 20 characters and each takes 3 bits. So this will be 60 bits. So size of the message will be 60 bits. And one more important thing we cannot neglect. What is that? When I am sending a message, suppose, encoded in this one, now how the receiver will know what are the codes? Even if I store it in a file and then later I want to retrieve, how do I remember what are the codes used? 00 means A only, that's it. See, for making it easy, I have taken the alphabets A to E here. Alphabets can be anything. This can be A, this can be M, this can be O, this can be Q. Then how I can know which code is for what? So I should also have the codes, that's this table also, along with the message. So this is encoded message, and this is the table. Use this table to decode the message. Yes. So message is 60-bit. Then you need the table also, the chart of codes that will help to decode this message. So let us see, you have to send this one also. How much size this will take? See, I have 5 alphabets. This alphabet should be in original form now. Now standard is what? ASCII code. So I must write ASCII code of all these. ASCII code of all these. So for this, 8 bits. So total how many? 5. So 5 into 8 bits. This is for what? Characters or symbols. Then for each 3-bit code, for A this is the code, B this is the code, for everything I should also have the code. So total how many? 5. And how many bits for each code? 3. So this is for codes. So this makes how much? This is 40 plus 15. This is 55. And what is the size of this original message? So message is 60 bits, right? And table or a chart of codes is 55 bits. So total how much this will be? 115 bits. Yes. So total size of the message along with the chart is 115 bits. It's not just 60 bits, it's 115 bits. No doubt the size of the message is something, but table is also important. So it was 160, now it became 115. So around 35 to 40% of reduction in size from 160 to 115. Right? So this is one method with fixed size codes. Now we'll go to variable size code and let us follow Huffman coding, which will still reduce the size of the message. Huffman encoding. Huffman says that we don't have to say take fixed size codes for the alphabets. Some characters or alphabets may be appearing few times, less number of times, and few may be appearing more number of times. So if you give small size code for the more appearing characters, then the size of the entire message will be definitely reduced. So let us see what is his idea. Already we have this table, all the alphabets, and how many times they are appearing in the message. So that gives the frequency of those alphabets. Now Huffman code follows optimal merge pattern. Now we have to generate our own code. So what should be the method for the code? So Huffman has given an approach for getting our own variable size codes. So he says that all those alphabets should be arranged in the increasing order of their count. So this is the least one, and this is the next one, and next one, and so on. So they are arranged in the increasing order of their count or frequencies. So the first, the smallest one, then the highest one. So this optimal merge pattern should be followed on this one. So what I should do? Merge 2 smallest one and make one node. So this is 2 plus 3, this is 5. Now next select 2 smallest and form a node. So 5, 4, 5, 6, these are remaining. Out of this which are 2 smaller, either I can take this 5, 4 or that 5, 4, so I will take this one. So I'll combine this one with this. So this is 9. Now what are the list I have, or the nodes I have? 9, 5, 6, these are the 2 minimum. So combine these 2, this is lamb. Then combine these 2, 2 are remaining now. So this one and this one. So this gives what? 20. So here we got our optimal merge pattern tree. It's actually follow optimal merge pattern, that is greedy approach. Always select 2 minimum 1, and we got this one. Now this tree will help us define the codes. How? On the left hand side edges, mark them as zeros, and on the right hand side edges, mark them as 1. That's it. Now what are the codes? For each alphabet, follow a path from root onwards. So for A, what is the code? 0, 0, 1. So A is 0, 0, 1. Then B is 1, 0, 1, 0. C, 1, 1, 1, 1. D, 0, 1, 0, 1. And E, 0, 0, 0, 0, 0, 0. That's it. These are the new codes we have. Now you can see some code is of 3 bits and one code is of 2 bits like that. So even we may have the codes with 1 bit also. Not here, in some examples. So variable size codes. Now, I can use these codes for encoding my message. Like B is 1, 0. C is how much? 1, 1. C is 1, 1. And A is 0, 0, 1. B is 1, 0. B is 1, 0. And D is 0, 1, 0, 1. Go on. If I use these codes, what will be the size of my message? So for that, how many bits are there for A? 3 bits. And how many times A is appearing? This is 3 into 3. 9. And 2 bits, and this is appearing for 5 times. So 5 into 2, 10. 2 bits, 1, 1, appearing for 6 times. So 6 into 2, 12. 2 bits appearing for 4 times. So 4 into 2, 8.
म्यूचुअल फंड तो सही है, तो कौन सा सही है ये डिसाइड करना बिल्कुल मेनू कार्ड खोल के कंफ्यूज होने जैसा है. लेकिन
And 3 bits appearing for 2 times, so 2 into 3 is 6. So for entire message, I have how many times each character is appearing and their sizes of codes I have taken, and I got this one. Now total number of bits are 45 bits. Size of the message is 45 bits. Means if I encode all, I just need 45 bits. So the message size is 45 bits. Now one more thing you should consider. Along with the message, I should also send this chart or a table or a tree. Then only decoding can be done. Means along with the encoded message, what is the codes, what are the codes used, that should also be there. Then only decoding can be done. So somehow this tree should be preserved or the table should be preserved. Or you can see what will be the size of the table. All these alphabets, I should send their ASCII codes, the standard code. So 8 bit of ASCII code. How many alphabets are there? 5. So this makes how many? 40 bits. Then codes also I should send. So these codes when they are stored. So how many codes are there? 5 codes, but what are the number of bits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is forming 12 bits. So together, this 40 plus that 12, so 52 bits are required for tree or a table. Tree or table. So what is the total size? Message is 45 bits and the table or a tree is 52 bits. And this will be 97 bits. Yes. Now you can see that it is still reduced from fixed size codes. So that's all about Huffman coding. Now if you want to know the size of the message at 45, you can know it from the tree also. How? See, this is the distance. How much is the distance? 1, 2, 3. And frequency is what? 2. So 3 into 2. So distance into frequency of each or count of each. You can take sigma, sum of all these. So this will be distance is 3 and frequency is 2 plus distance is 3 and frequency is 3 plus distance is 2 and the frequency is 4. Distance is 2, frequency 5. And distance is 2 and frequency is 6. So this is nothing but this calculation that we got, and this will be 45 bits only. So if you want to know what will be the size of the entire message from the tree also, you can find out by using this formula. If you refer a video on optimal merge pattern, you find that formula is defined. Let us see how decoding is done. This is the message now completely in the binary bits form. Follow the message. For this, you must have a tree for decoding. So start from root 0 left side, 0 left side, 1 right side. This is B. 0 0 0 1 complete. Then again start from the root 1 right side, again 1 right side. So reach the leaf, that is C. So these two are 1. Then again once you have reached the leaf, again start from the root 1 right side, 1 right side. So this is C. The next 0 left side, 1 right side. There's a D. So these two are complete. In this way, this message can be decoded, and from binary bits we can get back the original ASCII code. So the receiver can convert the message into ASCII code and use it in its machine. So inside the machine, while using, it will not be using the code, so it has to convert into ASCII codes. Like when you have any zip file or compressed file, you have to decompress for using it. Same way, it should be decoded and used. So that's all about Huffman coding.
ఇది హఫ్మన్ కోడింగ్ అనమాట. తర్వాత ఇది జ్ఞాప్స్నాక్ ప్రాబ్లం. జ్ఞాప్స్నాక్ అంటే ఇది కైండ్ ఆఫ్ షోల్డర్ బ్యాగ్, ఒక బ్యాగ్లో వేసుకునేది. ఇది విత్ ఏ లిమిటెడ్ వెయిటింగ్ కెపాసిటీ. అది కొంచెం దానికి ఒక కెపాసిటీ, ఇంత కెపాసిటీ అని చెప్పేసి పెట్టుకోవాలి. మనం ఒక ఐటమ్ 5 kgs, ఇంకొక ఐటమ్ 2 kgs అని ఇస్తాం. బ్యాగ్ వచ్చేసి 3 kgs 7 kgs లైక్ 6 kgs అట్లా మోస్తుంది. 5 kgs ఐటమ్ అంటాడు, కానీ దాని వాల్యూ ఇంత అని ఇస్తాడు. 2 kgs ఐటమ్ అంటాడు, దాని వాల్యూ ఇంత అని ఇస్తాడు. నువ్వు ఎంత ఆ వెయిట్ని వాల్యూస్ని పెట్టుకొని మనకు కొంచెం మోస్ట్ ప్రాబబుల్ వేలో వెళ్ళాలి. ఈ వెయిట్ ఈస్ ఎ కైండ్ ఆఫ్ షోల్డర్ బ్యాగ్ విత్ ఎ లిమిటెడ్ వెయిటింగ్ కెపాసిటీ, ఫ్యూయర్ టైమ్స్ హ్యావింగ్ సమ్ weight and value. Therefore there are two knapsack problems: fractional knapsack problem, 0 or 1 knapsack problem. Fractional అంటే నువ్వు ప్రతి దానిలో దాన్ని కట్ చేసి ఇంత తీసుకెళ్ళొచ్చు. 0 or 1 అంటే నువ్వు అయితే అసలు తీసుకెళ్ళకూడదు, లేదా ఒక దాన్ని తీసుకెళ్ళొచ్చు. Fractional knapsack problem is as the name suggests, its items are divisible here. For each item, compute is a value by weight. Arrange all the items in decreasing order of their value or weighting ratios. Put as many items as you can into the knapsack problem. Time complexity: if the items are already arranged in the required order, the while loop takes O of n time. Average time complexity of the quicksort is O of n log n. knapsack లో quicksort కూడా వస్తుంది. knapsack లో quicksort గురించి కూడా వస్తుంది. ఇప్పుడు ఎగ్జాంపుల్ ఏంటంటే ఆబ్జెక్ట్ 0 1 2 3 4 5, ప్రాఫిట్స్ P 10 5 15 7 6 18 30 3, వెయిట్స్ వచ్చేసి W 2 3 5 7 1 4 1 ఇట్లా ఉంది. ప్రాఫిట్ బై వెయిట్ రేషియో చూస్తే 5 1.3 3 1 6 4.5 3 ఉంది. ఇది 10/2 5 5 by 3 1.3, 5 by 15 by 5 3, 7 by 7 1, 6 by 1 6, 18 by 4 4.5, 3 by 1 1 ఇంట్లో వస్తుంది. ఎక్స్ వచ్చేసి 1 2 by 3 1 0 1 1 1, x1 x2 x3 x4 x5 x6 x7 అనమాట. ఎన్ వచ్చేసి 7, ఎం వచ్చేసి 15. సమ్మేషన్ ఆఫ్ xi ఇంటూ wi ఈజ్ ఈక్వల్స్ టు 1 ఇంటూ 2 ప్లస్ 2 by 3 ఇంటూ 3 ప్లస్ 1 ఇంటూ 5 ప్లస్ 0 ఇంటూ 7 ప్లస్ 1 ఇంటూ 4 ప్లస్ 1 ఇంటూ 1. ఇది వచ్చేసి 2 ప్లస్ 2 ప్లస్ 5 ప్లస్ 0 ప్లస్ 1 ప్లస్ 4 ప్లస్ 1 ఈజ్ ఈక్వల్స్ టు 15. సమ్మేషన్ ఆఫ్ ఎక్స్ ఇంటూ ప్రాఫిట్ 1 ఇంటూ 10 ప్లస్ 2 by 3 ఇంటూ 5 plus 1 into 15 plus 1 into 6 plus 1 into 18 plus 1 into 3, that is equals to 54.6. Constraints వచ్చేసి summation of xi into wi less than or equals to m. Objective వచ్చేసి max of xi into pi. ఇది స్నాప్స్కి సంబంధించి అనమాట. సో
यहाँ पर हमारे पास एक नैपसैक की प्रॉब्लम है. यहाँ
So many documents, spreadsheets, videos to go through, and the deadline is tomorrow. All the
Imagine we have a knapsack with a weight capacity of 9 kilograms. We also have a set of items, each with a specific weight and profit. Our goal is to select items in a way that maximizes the total profit while ensuring that the total weight does not exceed the knapsack's capacity. The term 0-1 in this problem means that we can either take an item completely or leave it entirely. We cannot take fractions of an item. This is different from the fractional knapsack problem, where we are allowed to take a portion of an item. I've already made a video on fractional knapsack. You can check it out. The link is in the description. A simple way to solve this problem is by using brute force. We start by either selecting the first item or skipping it. Then we repeat this process for the second item, and so on, until we reach the last item. This approach explores all possible combinations, which leads to an exponential time complexity. Because of this, it is highly inefficient and impractical for large inputs. Now, let's see how we can optimize this problem using the dynamic programming approach to make it more efficient. In this example, we have 5 items, each with a specific weight and profit. For ease of animation, let's set the knapsack capacity to 7. We will use the bottom-up approach to solve this problem. If you're not familiar with this approach, I recommend watching the video on Introduction to Dynamic Programming first. You can find the link in the description. First, we'll create a table where columns represent the weight capacities of the knapsack, rows represent the available items. Each entry in the table scores the maximum total profit achievable for a given capacity and the items considered so far. The first row and the first column represent the case where no items are available, so their values are set to 0. Now, let's start filling the table row by row, beginning with the first item. This item has a weight of 3 and a profit of 50. Looking at the first column, where the capacity is 1, the item's weight is 3, which exceeds this capacity, so we cannot place it in the knapsack, and we set the value to 0. Moving to the next column, where the capacity is 2, again, the item's weight is greater than the capacity, so we set the value to 0. Now for capacity 3, since the item's weight matches the capacity, we can store it. The profit for this item is 50. Since there are no previous items, we compare it with the value just above, which is 0, and take the maximum. So we update this cell to 50. For all remaining columns in this row, there are still no other items to consider, so we simply carry forward this value, which is 50. Thus, this row represents the case where only the first item is available. Now, moving to the second item, which has a weight of 2 and a profit of 4. We'll start filling the corresponding row. In the first column, the capacity is 1. Since this is less than the item's weight, we cannot place it in the knapsack, so we set the value to 0. Next, we move to the column where the capacity is 2. This can hold the current item. Comparing the current profit with the value above, we see that the current profit is 40, which is greater than 0. So we update this cell to 40 and move to the next one. Now the capacity is 3. The current item's weight is 2, with a profit of 40. However, the previous row already has a profit of 50, which is higher, so we keep the value as 50 and move to the next column. The capacity is now 4. The value from the row above is still 50, so we keep it at 50 as well. Now the next column has a capacity of 5. This one is interesting because it can hold both item 1 and item 2. Together, they give a total profit of 90, which is greater than the value from the row above. So we update this cell to 90. For all the remaining columns, we simply carry forward this value, as 90 is the best profit we can achieve so far. Now, moving on to the next item. It has a weight of 4 and a profit of 7. So we start filling this row. For columns with capacities up to 3, we simply copy the values from the row above, since the knapsack cannot hold this item. Now for the column where the capacity is 4, we compare the current profit, which is 70, with the profit from the row above, which is 50. Since 70 is greater, we update this cell to 7. Next, we move to the column with a capacity of 5. The current profit remains 70 because we cannot add anything else. This item alone weighs 4. However, the profit from the row above is 90, since it can hold both item 1 and item 2, whereas the current row can only hold item 3. So we update this cell to 90. Now, for the column where the capacity is 6, this can hold both item 2 and item 3, giving a combined profit of 110. Since this is greater than the previous 90, we update the cell to 110. Next, for the column with a capacity of 7, we can include item 3 and item 1. Together, they give a total profit of 120, which is higher than the previous value of 110, and certainly greater than the above value of 90. So, we update this cell to 120. Now we move on to the next item. The algorithm will similarly check whether the current profit is greater than the previous ones, and update the cells accordingly. I will pause the voiceover until the algorithm finishes. Once the table is generated, the last element represents the maximum profit value. In this case, it is 120. Now that we have found the maximum profit value, another problem is to determine which items were added to the knapsack using this table. This is very easy to find. We start by checking the element just above the last element. Here, the last element is 120, and the value above it is also 120. Since the value remains unchanged, this indicates that the current item is not making a difference. So, this item is not included in the knapsack. We continue checking the previous item. Again, the value above is the same, meaning this item is also not included. Next, we find an element where the value above is different. Here, the value above is 90, which means the current item is making a difference. This tells us that item 3 is present in the knapsack. Since this item has a profit of 70, it contributes 70 to the total profit. Now, subtracting 70 from 120 gives 50. We then look for 50 in the above row and continue performing the same steps to determine the remaining items. Here, the value in the cell above is also 50, which means the current item is not included in the knapsack. So, we move to the next item above. Now the value in the above cell is 0. This means the current item is making a difference and is included in the knapsack. So finally, we conclude that item 3 and item 1 are included in the knapsack. Now, the table contains n rows and w columns, and we need to traverse this table once. So both the time and space complexity here is big O of w times n. Check the GitHub link in the description to get the Python code for this problem.
Knapsack problem. In this video, I will explain what is 0 knapsack. The problem is 0 knapsack problem. In this video, I will explain what is 0 knapsack problem and how it can be solved using dynamic programming. We will understand its approach. Next, I will show you a tabular method for solving this one. Then also I will show you a sets method for solving this one. So there are two methods. We will see both the methods. First of all, let us understand what the problem is. Here I have some 4 objects. For each object there is some profit and there is some weight. And there is a bag of capacity M, that is 8 is given. The objective is to fill this bag with these objects. So can I put them all? See, the capacity 8 is 8, but the
How to generate Huffman code for this given data? Already we have constructed Huffman tree with this character and probability.
తర్వాత optical range merge pattern. Given an n number of sorted files, the task is to find the minimum computations done to reach the optimal merge pattern. When 2 or more sorted files are to be merged all together to form a single file, the minimum computations are done to reach this file is known as the optimal merge pattern. ఇప్పుడు ఇక్కడ ఆప్టిమల్ మర్జ్ అంటే ఇప్పుడు లిస్ట్ ఉంది x1 x2 x3 x4 x5 అనమాట. సైజ్ వచ్చేసి 20 30 10 5 10. ఫస్ట్ 95, అటు 1 ఇటు 1 35 60 35 2 2 15 20, తర్వాత 15 5 10 3 3, తర్వాత 60 2 2 30 30. The total cost of merging is summation of di into xi. Di is equals to distance of each node. The size of each node is equals to xi. So the total number of merging is 3 into 5 plus 3 into 10 plus 2 into 20 plus 2 into 30 plus 2 into 30 is equals to 205. Optimal merge pattern. Optimal merge pattern.
Yeah, the problem is optimal merge pattern. Again, this problem can be solved using greedy method, and if we know how to solve this problem, we can also understand Huffman coding. So let's talk about this one. Before knowing what is optimal merge pattern, first of all we should understand merging. Let us quickly understand merging. See, if I have a list A and B with some set of elements, if I have two sorted lists, then I have to combine them and get a third sorted list. Two sorted lists are there, I have to combine them. So the process is simple. What we do is we compare the first element of each, whichever is smaller we write on that, and then we move to the next element and compare these two, and 5 is smaller, we write that, 8 is smaller, 9 is smaller, 11, then 12 is smaller, then 16, then 20.
On Ticketed, invest in US stocks starting from $1.
So quickly I have shown you the elements are compared one by one, right? So one element from each side is compared, whichever is smaller than is written here, and we get a single sorted list. So merging can be done only on sorted list. How much time it has taken for merging? If I say this is M and this is N, then the total time is M plus N. If I count in terms of elements, 4 elements, and how many I got? 8 elements. So the total time taken depends on the size of the list. Now let us extend the problem. What happens if I have more than 2 lists? Let us look at it. Now here I have 4 lists given and their sizes are given. I have not taken the elements. I am saying that this list is having 6 elements and this is having 5 elements and so on. I have to merge these 4 lists. I can merge them together also, but that will be called as 4-way merging or n-way merging. No, I want to follow 2-way merging. So at a time I want to merge only 2 lists. So let us see how merging can be done. I'll take the list 6, 5, 2, 3. I'll merge these two first. So the new list what I get will be having 11 elements. Then this one with this one. So 11 plus 2 I'll be having 13 elements in this list. Then 13 and 3 I'll be having 16 elements. So final list altogether combined will be giving a 16 element list. Now you can see that at a time I'm merging 2 lists. But what is the total time spent in merging? Total cost. See, first I have merged 11 elements. So this is 11 plus then I have 11 merged 11 plus 2, so 13 elements, then 16. So I did not get the 16 element at once. It was in stages. So total amount of merging done is this one. So this is how much 40. Now, is there any other way I can merge? Let us try. A, B, C, and D. So this is 6, 5, 2, 3. I merge these two, 11. I merge these two, 5. Then I merge these two, 16. Yeah, I have selected a different pair every time. So what's the answer? Total cost is how much? 11 plus 5 plus 16. Total cost is correct. Is there any other way? Let me try. There may be many possibilities of merging, but I'll try one more. Now I merge from that side. First I merge these two. So I got 5. Then I merge these two, 10. Then I merge these two, 16. So total cost is how much? 16 plus 10 plus 5. 20, 31. Oh, I'm getting still less than that. So is there any other method by which I can get less than 31? I don't think so. See, if you see the different patterns, these are the patterns. One pattern, second and third pattern. Out of these 3 patterns, in this one I'm always selecting 2 smaller lists for merging. That's why I got the minimum result. So now from this observation, we can say that the greedy method that we should follow is always we should merge a pair of small size lists to get the best result. Yes, so we have the greedy method now. We got the approach for solving this problem. We understood that always you select 2 small size lists, combine them, then total merging time will be reduced. If you follow like this, then the time was 40 and so 32 and there's 31. So that is best one. Alright, so we'll take one problem and solve it. Here is an example problem for optimal merge pattern. I have a 5 files, x1, x2, x3, x5 are files, file names, and these are the sizes, the number of elements in each file. Now we'll follow greedy approach for solving this one. We have to find out a pattern in which the total cost of merging is minimized. So let us follow greedy method. Greedy method says that you should always select a smaller pair of files for merging. So they are not arranged in the increasing order of their sizes. I will take them in increasing order of their sizes. I have taken those files in the increasing order of their sizes. Now let us follow optimal merge pattern. So we should select a smaller pair of files and merge them, 5 and 10. So I'll merge these two. I'll get a new file of size 15. Then what are the files I have? I have a new file of size 15, 20, 30, 30. Now which one is smaller? I should select a pair. 15 and 20. These two are smaller. So I should select these two and merge them. So this is 35. 15 plus 20, 35. So after merging these two, I'll be getting 35 elements here. Now what are the list I have? 35, 30, 30. So I should select a pair of minimum size list or least size list. These two. Merge these two. It is 60. Now what are the list remaining? 35 and 60. Combine these two and form a list that is 95. Now let us find out what is the total cost of merging. See, first these two files are merged, the cost was 15, and when these are merged 35, so I should take the sizes in these circular notes. So the sizes are 15 plus 35 plus 95 plus 60 is 205. So the total cost of merging these files by following a optimal pattern is 205. I have added all these internal notes and I got this result. Even what I can do is, how I can know the process. This file, how many times it's merged? 1 time, 2 time, 3 times. So the number of times it is merged with the files depends on the distance. So let us call this as a distance. So distance how much? 1, 2, 3. So 3 times 5 plus 1, 2, 3. 3 times 10. 3 times 10 plus 1, 2. 2 times 20 plus 1, 2. 2 times 30 plus 1, 2. So 2 times 30. So I have taken their distances and their sizes. Even this total will also be 205. If you multiply and add all these things, it will be 205. So how I can know the total cost of merging? Either by adding the sizes of internal nodes or these nodes, external nodes I can say, external nodes with the distances. So here I can say it's like a formula, distance of each node di with the size of each node xi. So this gives the total cost of merging for all these files by using optimal merge pattern. That's all about optimal merge pattern. The problem is very simple, but this is used by Huffman code.
ఆప్టిమల్ మర్జింగ్ అంటే ఏం లేదు, రెండు షార్టేజ్ని కలుపుకుంటా లాంగ్ చేస్తే అదే ఆప్టిమల్ మర్జింగ్.
Huffman coding. So the next video will be about size of each node xi. So this gives the
లెవెల్స్తో సహా మల్టిప్లై చేయాలి. తర్వాత డైనమిక్ ప్రోగ్రామింగ్ it is uses as always of optimizing solutions, breakdowns of the complex it is used to solve the optimization solution, breaks down the complex of problem into the simpler sub problems, find optimal solutions to these sub problems, store the results of sub problems and sub problems memorization, reuse them so that the same sub problem is not calculated more than once. Finally, calculate the result of the complex problems, overlapping sub problems and optimal substructure. Type of dynamic programming: multi-staging graph, Colloid Schwarzschild, Bellman's Ford algorithms, 0 by 1 knapsack, optimal binary tree, reliability design, longest common subsequence LCS, matrix chain multiplication. Multi-stage graph is a data structure that is used to represent a graph in which the vertices are divided into a number of levels. The edge of the graph are also divided into a number of levels. The multi-stage graph is also called a hierarchical graph. ఇక్కడ ఉంది చూడడం, స్టేజెస్ 1 నుంచి 2కి, 2 నుంచి 5కి, 5 నుంచి 8, 3 6 7 4 5 8 అండ్ ఒకదాని నుంచి వేరే వేరే కూడా ఉంటాయి. సో ఇది టీ స్ట్రక్చర్స్. అండ్ ఫన్ ఎస్ కామా వి ఈజ్ ఈక్వల్స్ టు ఫంక్షన్ ఆఫ్ ఎస్ ఆఫ్ ఐ ప్లస్ వి సి ఆఫ్ కే అండ్ సో ఆన్ స్టేజెస్ అండ్ సమ్ సబ్ స్టేజెస్ మల్టిప్లాయిడ్స్ స్టేజ్ గ్రాఫ్స్.
The problem is multi-stage graph. This problem can be solved by applying dynamic programming strategy. In this video, I will explain you what is the graph problem. Second thing, how dynamic programming is applicable. Third thing, I will solve it using forward method. Let us start. Let us talk about the graph. A multi-stage graph is a directed weighted graph, and the vertices are divided into stages, such that the edges are connecting vertices from one stage to next stage only. First stage and the last stage will have just single vertex to represent the starting point, that is source or ending point or sink of a graph. This is usually useful for representing resource allocation. So here there are various paths from source to sink. I have to select the path which is giving me minimum cost. This is the objective of the problem. So it's a minimization problem, that is optimization problem. The problem can be solved using dynamic programming.
यूपीआई पिन फेल हो गया, इसलिए बर्तन मांजना पड़ रहा है.
Let us understand whether the dynamic programming can be applied on this one or not. So dynamic programming works on principle of optimality. Principle of optimality says that a problem must be solved in sequence of decisions. Let us see, can we solve this by taking sequence of decision? If I start from here, from first stage, that is stage 2 here, okay, in this stage I have to select one of the vertex. If I select 5, then I should make sure that what I am selecting is optimal, going to give me optimal result. Okay, once I selected this, now again I have two options here. From 5 I can go to 8 and 7. Out of this, again I have to decide and select anyone. Again next I have to decide and select anyone. So every stage I can take a decision. So yes, here the principle of optimality holds. Now applying dynamic programming procedure, that is tabulation method to get the data filled in the table. For each vertex I am going to find the cost, and for finding the cost I'll start from here. Because if you see from here, the edges are going that side. So if I want to find the cost of this one, then I should consider all the edges reaching till sink. If I find the cost of 3, then I should consider all the paths going till sink. If I consider 10, then the cost of path reaching there. Now if I say sink, then the cost is 0 obviously. So for the last vertex the cost is 0, and the vertex is 12 only. For the last vertex, how I got the cost as 0, I will write down this. Cost of 5th stage, vertex 12. So I will write here stage number and here the vertex number. And the cost is 0. This is how I will use the formula. Cost of 5, 12 means 5th stage and the vertex number 12. The cost is 0. Let us find out the cost of all these vertices in this 4th stage. So first, cost of stage 4, vertex 9. So what is the cost of reaching till sink? It is 4. This edge 4. Just a single edge path it is. So it is 4. And the cost of 4th stage, 10th vertex, it is 2. Cost of 4th stage, 11th vertex, this is 5. But this is 4 to 5, right? So from reverse 5 to 4. So this is 5, this is 2, and this is 4. Now by taking these vertices 9, 10 and 11, where I am reaching on 12th vertex only. So this is 12 and 12 and 12. Explain you what does it mean by D here, okay, very soon. Now let us take 3rd stage. So I have the vertices 6, 7 and 8. I'll find out the cost of these 3. So first 6. Cost of 3rd stage, 6th vertex. Now from here if I see, there are two edges coming out. So this is 6 to 9 as well as 6 to 10. So which one I should select? I should select the minimum cost. So let us consider both, then select the minimum. So I have to select minimum of what? cost of an edge 6 comma 9 plus cost of 4th stage 9th vertex, and also cost of an edge 6 comma 10 plus cost of 4th stage 10th vertex. I have to take the minimum of these two. So what is that? 6 plus cost of 9, 5 plus cost of 10. So 6 is what? This 6 to 9 is an edge. I'm writing it like this, right? C is cost of an edge. Cost is cost of an vertex. This is C is weight of an edge. Okay, I'm writing it as weight of an edge. 6 plus 9. So what is this equal to? Minimum of C 6 to 9 is how much? 6 plus cost of 4 comma 9 is here 4, comma C of 6 comma 10 is how much? 5, comma plus cost of 4 comma 10 is this one 2. So out of this, which one is smaller? This one is smaller. The vertex 10 has given me smaller value. 10 has given me smaller value. What is that? 7. So 6 is 7. And which vertex has given me minimum cost? Vertex 10. So the one which is giving minimum result, we have to write down that one here. Cost of 7 vertex, that's stage 3 here, cost of 3 comma 7. From 7 vertex, if you see there are 2 edges going out. So to know the cost of 7, I should know the cost of 9 and 10 plus the cost of this edge. So 4 plus cost of 9, 3 plus cost of 10. Out of those two, whichever is minimum, I should take that one. So I'll write like this: cost of an edge from 7 to 9 plus cost of a vertex 9 in 4th stage, comma cost of an edge from 7 to 10 plus cost of a vertex 10 in stage 4. Out of these two, I should take minimum. Now, if I take minimum out of these, cost of 7 to 9, edge 7 to 9 is 4, plus cost of 9th vertex is there from the table. So you can see how the values from the table are useful. So this 9, already you found out, now it is useful. It was useful for 6 also, now for 7 also, this value of 9 is useful. So this is what overlapping subproblems are there in dynamic programming. So 4, comma, C of 7 to 10, 7 to 10 is 3, plus cost of 10 is how much? 2. Out of these two, this is minimum, that is 5. So cost of a vertex 7 is 5. This we are getting due to which vertex? 10. So in D, I should write down 10. So in D, I should write down the vertex which has given me the shortest path, the minimum cost. Next is cost of 8. So there are 2 edges going out from 8 to 10 and 11. So cost of an edge from 8 to 10 and the cost of vertex 10 in 4th stage, comma, there's no space I write here, C of 8 to 11 plus cost of vertex 11 in stage 4. I have to take minimum of these. So this is minimum. I know these values, so I will replace them. Cost of 8 to 10, 5, plus cost of an edge 10, vertex 10, so 2, comma, cost of an edge 8 to 11, 6, plus cost of a vertex 11 is 5. Minimum is 7. Who has given the 7? Vertex 10 has given the 7. So here it is 7 and the vertex that has given that result is 10 only. Now let's find the cost of all those vertices which are in stage 2. Cost of vertex 2 in stage 2. See, there are 3 edges going out from here, 1 for 6, 1 for 7 and 1 for 8. So this is minimum of cost of an edge from 2 to 6 plus cost of vertex 6 in stage 3, comma, cost of an edge from 2 to 7 plus cost of a vertex 7 in stage 3, comma, cost of an edge from 2 to 8 plus cost of a vertex 8 in stage 3. First we are writing stage, okay? So I have located the cost function here itself, so out of these I have to take the minimum. See, this one is how much? Cost of an edge 2 to 6, 2 to 6 is 4 plus cost of 6 is 7, comma, cost of an edge 2 comma 7 is how much? 2 plus cost of this 7 is 5, comma, C of this one is 1 plus cost of a vertex 8 is 7. Out of these three, which one is smaller? This is 7 and this is 8 and this is 11. So 7 is smaller. So this one has given us minimum result. So the answer of this cost of vertex 2 is 7. And who has given us minimum result? The vertex 7 has given us minimum result, so this is 7. Cost of second stage 4th vertex is minimum of, from 4 there is only one edge, so cost of 4 comma 8 plus cost of vertex 8 in stage 3. Out of this there is only one value, so this is 11 plus cost of 8. 11 plus cost of 8 is 7. So this is 18. Who gave the answer? 8 has given the answer. This vertex has given the answer. So this is 18 and this is 8. Cost of second stage 5th vertex is minimum of, from 5 there are 2 edges, one is going to 7 and one is going to 8. So C of 5 comma 7 plus cost of 7th vertex in stage 3 plus, comma, cost of an edge from 5 to 8 plus cost of vertex 8 in stage 3. So out of this, minimum of C of 5 comma 7 is 11 plus cost of 7 is 5, comma, this one is 8 plus cost of 8 is 7. So this is 16 and this is 15. 15 is smaller, and who has given this result? 8. So this is 15 and this is 8.
We are handpicking only 150 students this year from across India for our flagship PG program in Startup Leadership. These 150 students will learn.
Now almost the table is filled here, only one value is remaining. Now we are at the stage to find the minimum cost for this, that is starting vertex. So that will give us the minimum cost from here to there, so to say. Cost of 1 comma 1 from vertex 1 in stage 1, that's first stage there, vertex. There are 4, 1 to 2 and 3 and 4 and 5. So I should consider all and take the minimum. Do I have the cost of vertex 2, 3, 4, 5? Yes, already they are filled here. So that is easy for solving now to find this cost. So this is cost of an edge from 1 to 2 plus cost of 2 to 2, comma, cost of an edge from 1 to 3 plus cost of third vertex in stage 2. This, what is minimum? Let us find out. See, the values are 9, 7, 3, 2, right? So this is 9 plus cost of 2 comma 2 is 7, comma, cost of 1 comma 3 is how much? 7 plus cost of vertex 3 is 9, comma, cost of this vertex 1 comma 4 edge is how much? 3 plus cost of 4 is 18, comma, cost of 1 comma 5 is 2 plus cost of 5 is 15. Out of this, which one is smaller? This is 16, this is also 16, this is 21 and this is 17. So I got two answers that are same. So the answer is 16 only, but that is going via what? First was vertex 2 and second was vertex 3. Both are giving same result, so I write 2 or 3 here. I can take only one also, but I'm writing both to see how the difference will be. It's like first filling the smaller values, then getting the answer for the larger value. So we started from the backwards side, that is from the back side of our multi-stage graph, last stage onwards we started. But still this is called as forward method. How? We will see that next. Let us frame the formula now. I did not show you the formula, but now, the procedure already have shown you. Let me frame the formula. We were finding it like this. Cost of ith stage, jth vertex. This I is a stage number, right? And this j is a vertex number. So this was minimum of, I was taking minimum of what? This was cost of an edge from vertex j to some vertex l plus cost of that next vertex l. If I say j and l, j is supposed to, then l is supposed 6. So cost of 2 to 6. Then the cost of 6, third stage 6 vertex. So we were writing the stage number here, I plus 1 and l. This is for the formula we were finding. Whatever the edges are available, for 2 there are 3 edges. So we wrote the same thing 3 times. You can see that for finding cost of second stage third vertex was minimum of, one of the value I will write down, third vertex to sixth vertex plus cost of third stage sixth vertex. If I say this is stage number 2 and vertex, this is j, then minimum of cost of an edge j to some l, some vertex l. Then cost of that l, and that L6 is definitely in the next stage. So this is I plus 1. If I is a 2, then this is 2 plus 1. So this is I plus 1. This is how we are using the formula for finding these costs in multi-stage graph. So this is the formula for multi-stage graph. And we say that j and l belongs to set of edges and l belongs to next stage. So this is the formula that you can find in the textbooks. Now the actual dynamic programming starts, right? Already we have the formula and filled up the table based on the dynamic programming approach to get the result. Actually, the method of dynamic programming is to solve the problem by taking sequence of decisions. We have not taken any decision so far, but now we are going to take the sequence of decision based on the data available. So already I was writing the d value, whichever the vertex was giving us minimum result, I was writing the d value there. Using that we take a decision. What decisions we take? From here where we should go, to which vertex, then from there where we should go, then from there where we... So decisions are taken, only have the complete data with you. So already we have the data. Now we are going to solve it by taking sequence of decision, and we will start from vertex 1 onwards towards sync. So this is forward. The decisions will be taken in forward direction. So the based on decisions, this is forward method. Let me do that. First of all, distance of d values I have for 1, 2, 3, 4, all I have. So first I will write stage number. This is a stage number, right? And then I will write on vertex. This is vertex. D of 1, 1. So actually we are concerned about this. I'm writing it like a formula, okay? So this is stage number and this is vertex number. So we will consider this vertex number. What is the answer? 2. So let us take 2. Now in the second stage, already we have taken 2. D of 2, 2. Since this was the first stage, we selected first vertex. In second stage, second vertex, vertex 2. Now from there where we should go? So 2, who has given the minimum result for 2? 7. So this is 7. In D we have 7. Now we are on the 7th vertex on 7th vertex in stage 3. Now being on stage 3, where we should go next, on 9 or 10? Which one? So 7 has given us a 10. So 10. Now we are on the vertex 10 in stage 4. Then from 4th stage, 10th vertex, where we should go next. So table will tell us everything, so we should go on 12. So that's it, 12. So our path is what? We started from vertex 1 to 2, then 7, then 10, and 12. So this 1 to 2, 2 to 7, 7 to 10, 10 to 12. This is the shortest path from source to sink. That this d values has given us the result. So now we have taken sequence of decisions. Let me show you once more. For 3, I said that for both 2 and 3 we got the answer as 16. So let us 3, what does it give? I'll start from vertex 1, then stage 1. So 1, 1 gives us what? 3. Then I'm on the stage 2 on vertex 3, then third vertex. What's the one which has given minimum result? 6. So this says goes to 6. Then in the third stage, I'm on vertex 6 now. So, okay, I'll do it here also. I have gone to 3, then 3 has sent me to 6. Now being on third stage, 6th vertex, where I should go next? So 6. What's the answer? 10. So go to 10. So it says that I should move to this one. So this is the decision I have taken. Then 10 is in 4th stage. So from 10th vertex, where I should go? 10th vertex, we already have seen this answer. That is 12. 12. So from 10, I should go to 12. So this is another route you see. This is another route, which is giving us the minimum result. So this is 1. Right? So I have 2, 7, 10, then 1, 3, 6, and 10 and 12. So I have 2 paths of same cost. So the optimal result is only 1. But in by chance, we are having 2 paths which are giving us the same result. That's all about multi-stage graph problem. And I have explained you how dynamic programming is followed here.
So many documents, spreadsheets, videos to go through, and the deadline is tomorrow. All the trainees are stressed. Everyone except Sandra. Because with Google AI Plus, she can just use Notebook LM to create a simple podcast summary. Catch up fast.
यार ये क्या हो गया? फ्रिज पूरा एम्प्टी, न वेजिटेबल्स न फ्रूट्स, और टाइम देखो, गेस्ट आने ही वाले हैं. अभी वेजिटेबल्स एंड फ्रूट ले.
The problem is multi-stage graph. Already I have one video.
It's Warshall. Floyd's Warshall. This strategy is adopted by Floyd-Warshall algorithm is a dynamic programming. The running time of the Floyd-Warshall algorithm is determined by the triply nested for loops for lines 3 to 6. Each execution of line 6 takes off one time. The algorithm runs in a time of theta of n cube. ఇక్కడ 1 నుంచి 4కి, 4 నుంచి 2కి, 3కి, అండ్ 2 నుంచి 3కి 8 ఇన్ఫినిటీ. ఇక్కడ ప్రాబ్లమ్స్ ఉన్నాయి. అండ్ ఆ తర్వాత ఈస్ట్ కాంప్లెక్సిటీ ఆఫ్ ఎన్ క్యూబ్, స్పేస్ కాంప్లెక్సిటీ ఆఫ్ ఎన్ క్యూబ్.
The problem is solved by a shortest path. In this video, we will look at a problem and we will solve it using that.
Let's understand how the Floyd-Warshall algorithm finds the shortest path between any two pairs of nodes in the graph. Earlier, we've seen single-source shortest path algorithms like